Drifting far beyond the familiar glow of Earth, the most distant satellites humanity has ever launched have become cosmic scouts, revealing secrets of the universe we could once only imagine. From the icy edge of our solar system to the interstellar void, these robotic explorers have uncovered ancient whispers of creation, mysterious energy fields, and even hints about what lies beyond the reach of our sun's influence, expanding not just our knowledge, but our sense of where we truly belong in the cosmos. Join us as we explore what they have discovered. Closer than ever, Parker Solar Probe's radical approach to the Sun. Designed to fly closer to the Sun than any mission before it, the Parker Solar Probe is rewriting what we know about our star. It is venturing into a zone that no human-made object has ever reached, a place where temperatures soar higher than the surface of Venus and solar radiation could melt most known materials. Yet, the Parker Solar Probe continues its journey, sending back data that is changing our understanding of the Sun and its influence on the solar system. Previous solar missions, such as NASA's Helios spacecraft in the 1970s, came within 43 million kilometers of the Sun. That was an impressive feat at the time, but Parker Solar Probe has shattered that record. With each orbit, it moves closer and closer. On December 24th of 2024, it was just 6.1 million kilometers from the Sun's surface. That is nearly 7 times closer than any spacecraft before it. At that distance, the Sun's gravity is pulling the probe with incredible force, causing it to travel at speeds of nearly 700,000 kilometers per hour, making it the fastest human-made object ever. The spacecraft is built for survival. One of its most critical features is the heat shield, a thick layer of carbon composite material designed to withstand temperatures of nearly 1,400 degrees Celsius. This shield, known as the thermal protection system, allows the probe to face the Sun while keeping its scientific instruments at a safe operating temperature. Without this shield, the spacecraft would not last more than a few seconds in the extreme heat and radiation. As it moves closer to the Sun, it encounters intense bursts of energy and streams of charged particles moving at incredible speeds. The Sun's outer atmosphere, known as the corona, is a chaotic and highly dynamic region. One of the biggest mysteries of the Sun is why the corona is so much hotter than the surface. The Sun's surface, or photosphere, has an average temperature of about 5,500 degrees Celsius, but the corona reaches temperatures of several million degrees. This seemingly illogical temperature difference has puzzled scientists for decades, and Parker Solar Probe is helping to uncover the reasons behind this strange phenomenon. Unlike missions to the outer solar system, which require years of travel to reach their destinations, Parker Solar Probe benefits from the Sun's immense gravity. However, getting close to the Sun is not as simple as just pointing a spacecraft toward it. Earth is moving around the Sun at an incredible speed, and any spacecraft launched from Earth carries that motion with it. To fall toward the Sun, the probe had to slow down its forward motion, which required an extremely powerful rocket. NASA used the Delta IV Heavy rocket, one of the most powerful rockets in operation, to launch the spacecraft in 2018. Even then, getting close to the Sun required a clever strategy. Instead of flying directly toward the Sun, the spacecraft uses the gravity of Venus to gradually adjust its orbit. Over the course of 7 flybys of Venus, the probe's path is carefully shaped, allowing it to move closer with each pass. Communication with the Parker Solar Probe is a delicate task. Because it is moving so fast and so close to the Sun, there are times when direct communication with Earth is not possible. The spacecraft is designed to operate autonomously, making split-second decisions to protect itself and ensure that it continues collecting valuable data. It has sensors that constantly monitor its position relative to the Sun, making adjustments as needed to keep its heat shield correctly aligned. If anything unexpected happens, the probe has built-in safety measures that allow it to correct itself without waiting for instructions from Earth. Unlike missions to planets and moons, where spacecraft often send back detailed images, Parker Solar Probe's primary goal is not photography. Instead, It is measuring the sun's electric and magnetic fields, capturing the movement of charged particles, and detecting waves of energy flowing through the corona. The data it gathers is helping scientists understand how solar storms form and how the sun's activity influences Earth. When the sun releases bursts of charged particles, known as solar wind, these particles travel through space at incredible speeds. If a strong solar storm hits Earth, it can disrupt satellites, damage electrical grids, and even pose risks to astronauts in space. By studying these events up close, Parker Solar Probe is providing critical information that could help predict solar storms and protect technology and people from their effects. One of the most exciting discoveries so far is the detection of unexpected waves and reversals in the solar wind. These strange movements, known as switchbacks, were not well understood before Parker Solar Probe got close enough to observe them directly. The mission has also provided new details about the sun's magnetic field and how energy is transferred within the corona. Each new piece of data brings scientists closer to answering some of the most fundamental questions about how stars like the sun work. Illuminating the solar corona, unraveling the sun's outer atmosphere. One of the most important discoveries the Parker Solar Probe has made so far is about the structure of the corona. Before this mission, scientists thought of the corona as a relatively smooth and continuous layer of plasma. However, the Parker Solar Probe has shown that the corona is more like a turbulent sea of energy. Instead of a uniform layer, it is filled with constantly shifting magnetic fields and waves of charged particles moving at incredible speeds. Normally, in space, the farther something is from a heat source, the cooler it gets. This is true for campfires, ovens, and even planets. But the corona defies this rule, capable of reaching over 1 million degrees. This means that something inside the corona is adding enormous amounts of energy. Scientists have suspected for a long time that magnetic fields play a role in this process, but they never had direct measurements from inside the corona itself until now. The Parker Solar Probe's instruments have shown that the corona is filled with bursts of energy, sudden waves of plasma, and strange magnetic structures that twist and turn unpredictably. One of the biggest surprises has been the discovery of rapid and frequent reversals in the sun's magnetic field, known as switchbacks. These switchbacks were detected in the solar wind, but their origin was unknown. Parker Solar Probe found that they come from deep within the corona itself, where powerful magnetic forces shape the flow of energy. Scientists now believe that these rapid magnetic shifts help to accelerate the solar wind, giving it the energy it needs to escape the sun's gravity and reach speeds of over 1 million kilometers per hour. By understanding these switchbacks, researchers can get closer to solving one of the biggest mysteries in solar science: how the solar wind is powered. The sun is not always calm. Sometimes it releases massive bursts of energy in the form of solar flares and coronal mass ejections. These events send billions of tons of charged particles racing through space. Understanding how these eruptions form is crucial for predicting space weather and protecting modern technology. During its close passes, Parker Solar Probe has flown through some of these coronal mass ejections, which no spacecraft has ever done before. The data has shown that these ejections are more structured than previously thought, with complex layers of magnetic fields and plasma that expand as they move outward. By studying the detailed structure of these events, scientists hope to improve their ability to predict when and how they will affect Earth. When viewed in visible light during a solar eclipse, the corona looks like smooth streamers of glowing gas. But when seen in ultraviolet or X-ray light, it appears as a chaotic network of bright active regions surrounded by dark, cooler areas. Parker Solar Probe is helping to explain these differences by revealing the small-scale structures that create them. It turns out that the corona is filled with fine loops of magnetic energy, some of which release their energy quickly, while others store it for longer periods. This creates the different patterns seen in various types of light. One of the most exciting findings has been the confirmation that tiny explosions, known as nanoflares, may be responsible for much of the corona's heat. These are too small to be seen directly from Earth. Each nanoflare releases a sudden burst of energy, heating the plasma around it. Though each individual event is small, there are so many of them happening across the Sun at any given time that they could collectively be responsible for the extreme heat of the corona. The Sun's magnetic field is enormous, stretching far beyond the orbits of the planets. This field is not static. It is constantly shifting and changing as the Sun's internal processes generate new magnetic structures. These changes influence the entire solar system, affecting everything from space weather to the movements of charged particles in interstellar space. By flying through the corona, Parker Solar Probe is providing the most detailed measurements yet of how the Sun's magnetic field connects to its outer atmosphere and how it extends into space. Solar winds and space weather. Unexpected dynamics near the Sun. Unlike wind on Earth, which is made up of moving air, the solar wind consists of charged particles, mostly electrons and protons, that are constantly ejected from the Sun's outer layers. When the solar wind reaches Earth, it interacts with the planet's magnetic field, creating spectacular auroras near the poles. But it can also cause serious problems. During periods of intense solar activity, the solar wind can become much stronger, triggering harmful space weather events. Before the Parker Solar Probe, scientists could only study the solar wind from a distance. Most observations were made from spacecraft located far from the Sun, where the solar wind had already traveled millions of kilometers. But these distant measurements could only reveal part of the picture. By the time the solar wind reached these spacecraft, it had already been shaped by other forces in space. What scientists needed was a way to study the solar wind at its source before it had changed and evolved. Parker Solar Probe has made this possible. Instead of a smooth, steady stream of particles, Parker Solar Probe has found that the solar wind is full of sudden changes and bursts of energy. These bursts, called plasma waves, seem to be linked to the Sun's magnetic field. The probe's instruments have detected sharp switchbacks in the direction of the magnetic field. Scientists now believe that these switchbacks in the solar wind may play a role in shaping space storms that affect planets and spacecraft. If a burst of solar wind with strong switchbacks reaches Earth, it could cause sudden changes in the planet's magnetic field, leading to disruptions in our power and communication infrastructure. Understanding how these switchbacks form and how often they occur could help scientists predict space weather events with greater accuracy. Another key finding from Parker Solar Probe is that there appear to be different types of solar wind, each with its own characteristics. Some regions produce faster, more energetic streams of particles, while others generate slower and more stable flows. In some areas, open magnetic field lines allow particles to escape more easily, creating fast solar wind. In other areas, closed magnetic loops trap plasma, leading to slower, more variable streams of particles. For years, researchers believed that the solar wind was mostly shaped by large-scale processes happening deep within the Sun. But Parker Solar Probe has shown that much of the solar wind's complexity comes from small-scale interactions happening in the corona. The probe's instruments have detected tiny magnetic explosions, wave-like motions in the plasma, and high-energy bursts of particles that all play a role in shaping the solar wind's behavior. As humanity moves towards sending astronauts beyond Earth's protective magnetic field, exposure to solar radiation becomes a major concern. The solar wind carries energetic particles that can be dangerous to both astronauts and spacecraft. During periods of intense solar activity, these particles can become even more hazardous, increasing the risk of radiation exposure. By studying the solar wind up close, Parker Solar Probe is helping scientists develop better ways to protect astronauts on future missions to the Moon, Mars, and beyond. As it moves outward from the Sun, the solar wind collides with planets, moons, and even distant interstellar space. On planets like Mercury, which has a weak magnetic field, the solar wind directly bombards the surface, stripping away particles and creating a thin, temporary atmosphere known as an exosphere. On planets with stronger magnetic fields, like Earth and Jupiter, the solar wind creates vast magnetic storms that can produce auroras and influence planetary weather. Scientists are now using Parker Solar Probe's data to refine models of how the solar wind interacts with space. By comparing the probe's close-up measurements with data collected from spacecraft further away, researchers can track how solar wind changes as it moves outward. This is helping to create a more complete picture of how the Sun's activity affects the entire solar system. Galileo's Grand Tour, a fresh look at Jupiter's complex system. Launched by NASA in 1989, the Galileo spacecraft spent nearly 8 years traveling through space before reaching its final destination, Jupiter, the largest planet in the solar system. Unlike previous missions that had only flown past the gas giant, Galileo became the first spacecraft to enter orbit around Jupiter, allowing it to study the planet and its surrounding system for years instead of just days. Jupiter is a planet of extremes. It is more than 300 times more massive than Earth and is made mostly of hydrogen and helium, similar to the Sun. Its thick atmosphere is home to the largest storm in the solar system, the Great Red Spot, which has been raging for centuries. Below its swirling clouds, scientists believe a dense liquid metallic hydrogen layer exists, creating the planet's powerful magnetic field. Galileo was designed to investigate these mysteries up close, sending back detailed data that revealed the true complexity of Jupiter's system. One of Galileo's most dramatic moments came early in its mission, when it released a probe into Jupiter's atmosphere. This small, unmanned craft plunged into the planet's clouds at high speed, sending back data as it descended. For nearly an hour, it transmitted measurements of temperature, pressure, and wind speeds before being crushed and vaporized by the immense forces inside the planet. The data it gathered showed that Jupiter's winds were far stronger than expected, with powerful jet streams moving at speeds of more than 600 kilometers per hour. It also revealed that the atmosphere was drier than scientists had predicted, with lower amounts of water than expected. These findings challenged existing theories about how Jupiter formed and forced scientists to rethink their understanding of gas giants. While Galileo's study of Jupiter's atmosphere was groundbreaking, some of its most exciting discoveries came from its exploration of the planet's moons. Jupiter has dozens of moons, each with unique features, but 4 of them stand out as the most remarkable: Io, Europa, Ganymede, and Callisto. These large moons, known as the Galilean moons, were first discovered by Galileo Galilei in 1610, but it wasn't until the spacecraft bearing his name arrived in orbit that their secrets began to be revealed. Io, the closest of the 4 moons to Jupiter, turned out to be the most volcanically active world in the solar system. Galileo's instruments detected massive eruptions on its surface, with plumes of molten rock shooting dozens of kilometers into space. Unlike volcanoes on Earth, which are powered by heat from the planet's core, Io's volcanic activity is caused by the immense gravitational forces of Jupiter and the other moons. These forces stretch and squeeze Io's interior, generating enormous amounts of heat and driving continuous eruptions across its surface. Europa, the second Galilean moon, quickly became one of the most intriguing objects in the solar system. Galileo's images showed that Europa's surface was covered in a thick shell of ice. But beneath that ice, scientists believe there is a vast ocean of liquid water. This ocean could be more than 100 kilometers deep, holding more than twice the amount of water found on Earth. What makes this discovery so important is the possibility that Europa's ocean might support life. Deep in Earth's oceans, life thrives around hydrothermal vents, where heat from the planet's interior provides energy in the absence of sunlight. If similar vents exist on Europa's seafloor, they could create an environment where extraterrestrial life might exist. Some scientists believe that primitive organisms, similar to bacteria found in Earth's deep oceans, might already exist there. Galileo's data provided the first strong evidence for this hidden ocean, sparking plans for future missions to explore Europa in more detail. Ganymede, the largest moon in the solar system, also revealed surprises. The probe discovered that Ganymede has its own magnetic field, something no other moon in the solar system has. This suggests that Ganymede has a partially liquid core, generating a magnetic field similar to Earth's. The spacecraft also detected evidence of subsurface water on Ganymede, raising the possibility that it, too, could have an ocean beneath its icy crust. Later observations by the Hubble Space Telescope provided more evidence that Ganymede's ice shell might be floating on top of a deep, salty ocean. Unlike Europa, where the ocean may be in contact with the rocky seafloor, Ganymede's ocean is thought to be trapped between layers of ice. This makes it less likely to have the same hydrothermal activity that could support life, but the presence of liquid water still makes it an intriguing world to study. Callisto, the outermost of the Galilean moons, turned out to be very different from the others. While Io, Europa and Ganymede showed signs of active processes shaping their surfaces, Callisto appeared to be a much older and more heavily cratered world. Galileo's instruments detected a magnetic signature around Callisto that suggests the presence of a conductive layer beneath the surface. If this is a salty ocean, it could be one of the deepest and oldest in the solar system. Beyond the moons, Galileo provided groundbreaking insights into Jupiter's magnetic environment. The planet has the most powerful magnetic field in the solar system, creating a vast region of charged particles known as the magnetosphere. This magnetosphere extends millions of kilometers into space, interacting with the solar wind and shaping the environment around Jupiter. Galileo's instruments revealed that this region is far more complex than previously thought, with intense radiation belts and electric currents that affect the entire system. Scientists had long known that the planet's magnetosphere was immense, but Galileo showed that it was even larger than expected, sometimes stretching as far as Saturn's orbit. This means that Jupiter's influence extends far beyond its immediate surroundings, shaping the space environment of the outer solar system. Throughout its time at Jupiter, Galileo made multiple flybys of the planet's moons, each time sending back new data that reshaped scientists' understanding of these worlds. It faced harsh conditions, including intense radiation that gradually damaged its systems. Despite this, the spacecraft continued to operate for years, providing an unprecedented look at Jupiter's complex system. After more than a decade in space, Galileo's mission came to an end in 2003. NASA decided to send the spacecraft on a final dive into Jupiter's atmosphere, ensuring that it would not accidentally crash into and contaminate one of the potentially habitable moons like Europa. As it plunged into the planet's clouds, Galileo sent back a final burst of data before being destroyed by the extreme pressures inside Jupiter. The mission laid the foundation for follow-up missions like Juno, which is now studying the planet's interior and magnetic field, and the upcoming Europa Clipper, which will investigate Europa's ocean in more detail. The data gathered by Galileo remains a crucial source of information, helping scientists understand not only Jupiter, but also the nature of giant planets throughout the universe. Jupiter's magnetic enigma: new perspectives on planetary magnetospheres. Unlike Earth's magnetic field, which is relatively simple and shaped like a bar magnet, Jupiter's magnetic field is immense, irregular, and constantly shifting. It extends millions of miles into space. This magnetosphere is the largest structure of its kind, stretching so far that if it were visible to the human eye, it would appear larger than the full moon in the night sky. Unlike earlier spacecraft, Galileo carried instruments designed to measure the strength and shape of Jupiter's magnetic field, as well as how it interacted with the surrounding space. One of the most surprising discoveries was that Jupiter's magnetic field is not symmetrical. On Earth, the north and south magnetic poles are positioned relatively close to the geographic poles. But on Jupiter, the magnetic field is tilted, and its strength is much stronger in some areas than in others. One side of the field extends deeper into space, while the other seems compressed. This unusual shape suggests that Jupiter's internal magnetic field is generated in a way that is different from Earth's. Scientists believe that Earth's magnetic field is produced by the movement of molten iron in its outer core. But Jupiter doesn't have a solid surface or a metallic core like Earth's. Deep inside Jupiter, the immense pressure forces hydrogen into a state where it acts like a metal, conducting electricity and creating a magnetic field. Unlike Earth's core, which has a relatively stable structure, Jupiter's interior is in constant motion. This movement could explain why its magnetic field is so irregular and changes over time. One of the most dramatic features of Jupiter's magnetosphere is the way it interacts with its moons. The most extreme example is Io. Io's massive eruptions send plumes of gas and dust high into space. These volcanic eruptions release sulfur and other materials that become trapped in Jupiter's magnetic field, forming a giant ring of charged particles around the planet. This region, known as the Io plasma torus, is a vast glowing belt of energized particles that constantly interact with Jupiter's magnetosphere. As Io moves through this environment, powerful electrical currents form between the Moon and Jupiter. These currents generate massive bursts of radio waves that can be detected from Earth. They also create lightning-like flashes in Jupiter's atmosphere, where the charged particles enter the planet's magnetic field. Galileo's instruments detected these electrical interactions, providing new evidence of how Jupiter's magnetic field influences its moons and the space around it. The outer edge of Jupiter's magnetosphere is where the planet's influence meets the solar wind. When solar wind particles reach Jupiter, they encounter the planet's magnetic field, creating a shockwave similar to how water flows around a rock in a river. This boundary, known as the bow shock, marks the point where the solar wind slows down and begins to move around Jupiter's magnetosphere. Galileo's observations revealed that this boundary is not fixed. Instead, it shifts back and forth as the strength of the solar wind changes. Sometimes, intense bursts of solar activity can compress Jupiter's magnetosphere, forcing it closer to the planet. Other times, the magnetosphere expands outward, creating a vast region where Jupiter's magnetic field dominates. This constant movement affects the entire system, influencing the behavior of charged particles, radiation belts, and even auroras in Jupiter's upper atmosphere. Jupiter's auroras are some of the most powerful in the solar system. Unlike Earth's auroras, which are caused by charged particles from the Sun interacting with the atmosphere, Jupiter's auroras are powered by its own magnetosphere. The intense radiation and electrical currents generated within the magnetosphere create glowing bands of light around the planet's poles. Galileo's data showed that these auroras are constantly changing, sometimes forming bright, swirling patterns that shift over time. Some of Jupiter's auroras were discovered to be influenced by its moons. Scientists found that Europa and Ganymede in particular leave a distinct signature in Jupiter's auroras. As these moons move through the magnetosphere, they create electrical connections that leave behind glowing footprints in the planet's atmosphere. These footprints travel along Jupiter's magnetic field lines, forming bright spots of light near the poles. Jupiter's magnetic field also plays a role in trapping high-energy radiation around the planet. The region known as Jupiter's radiation belts contains some of the most intense radiation in the solar system. These belts are filled with fast-moving electrons and other charged particles that spiral along Jupiter's magnetic field lines. The radiation in these belts is so strong that it can damage spacecraft electronics and even pose a risk to future human missions if they ever venture to the outer planets. Galileo had to be specially designed to withstand this radiation. It carried shielding to protect its instruments, but even with these precautions, some of its systems were affected by the intense radiation over time. The spacecraft's discoveries about these radiation belts helped scientists understand how Jupiter's magnetic field interacts with the space around it, and how similar environments might exist around other planets. Cassini's Saturn. Sojourn. rewriting the narrative of planetary rings. Before Cassini, Saturn's rings were often thought of as relatively static features, vast icy structures that had remained largely unchanged for millions of years. But as the spacecraft made repeated passes through Saturn's ring system, it revealed that these rings were anything but stable. Instead, they were dynamic, constantly shifting and evolving in response to a variety of forces, from Saturn's gravity to interactions with its moons, and even collisions between ring particles. Early observations from Earth and past missions like Voyager had suggested that the rings were made up of countless small particles ranging in size from tiny ice grains to massive boulders. What Cassini found was that these particles were in constant motion, forming waves and patterns that rippled through the rings like waves on an ocean. Some of these waves were caused by Saturn's moons, which exerted gravitational forces that pulled on the ring material. Others were created by unseen processes, hinting at new dynamics that scientists are still working to understand. Cassini's detailed images showed structures within the rings that had never been seen before. Among them were propellers, features that appeared when larger objects, possibly moonlets, moved through the rings. These moonlets were too small to be directly observed, but their presence was revealed by the disturbances they created, carving out distinctive gaps in the surrounding material. These propeller-like shapes provided clues about how moons might form within the rings and how similar processes could be at work in other planetary systems. Scientists had long debated whether the rings had formed along with Saturn, or if they were a more recent addition to the planet. Cassini's data suggested that the rings may have formed only a few 100 million years ago, relatively recent on cosmic timescales. This raised new questions about how the rings formed and whether they might eventually disappear. If the rings are indeed young, it suggests they could have been created by the breakup of a large icy moon or the capture of a passing comet that was torn apart by Saturn's gravity. Cassini also showed that the rings are shedding material into Saturn's atmosphere at a faster rate than expected. Tiny particles from the rings are slowly drifting inward and falling into the planet, creating a phenomenon known as ring rain. This process, which was measured directly by Cassini during its final orbits, suggests that the rings might be disappearing over time. If this continues, the rings could eventually fade away, leaving Saturn looking very different from how it appears today. Cassini's instruments detected variations in the makeup of different ring sections, revealing regions that were richer in ice and others that contained more dust and rock. Some parts of the rings appeared brighter and purer, while others were darker and more contaminated, possibly from debris that had fallen in from the surrounding environment. This suggested that the rings were not only changing in structure, but also in composition, affected by ongoing collisions and interactions with the space around them. The spacecraft's data also provided insight into the interactions between the rings and Saturn's many moons. Some moons, like Pan and Daphnis, orbit within gaps in the rings, acting as shepherds that help keep ring particles in place. These moons create wave-like disturbances in the ring material as they pass, sculpting the edges of the gaps they inhabit. Other moons, like Enceladus, actively contribute material to the rings. Cassini discovered that Enceladus, which has geysers spewing water vapor from beneath its icy crust, was feeding icy particles into Saturn's E-ring, adding to its material over time. Cassini observed that changes in the Sun's activity could alter the appearance of the rings, causing some areas to brighten or darken depending on the level of sunlight they received. This hinted at a connection between the rings and space weather, showing that they were not isolated structures, but part of a larger system, influenced by the environment beyond Saturn itself. Cassini's final orbits, known as the grand finale, allowed scientists to gather the most detailed measurements ever taken of the rings. As the spacecraft made a series of daring dives between the rings and Saturn, it provided close-up data on their structure and composition. The discoveries made by Cassini have reshaped our understanding of planetary rings, not just at Saturn, but throughout the solar system. The insights gained from this mission have have helped scientists better understand the formation and evolution of ring systems around other planets, including the thin rings of Jupiter, Uranus, and Neptune. Cassini's observations have also provided clues about how rings might form around exoplanets in distant star systems, offering a new perspective on how common these features might be in the universe. The mystique of Titan and Enceladus. Clues from Saturn's moons. Saturn's moons have long been a source of fascination, but it was the Cassini mission that transformed them from distant, mysterious worlds into some of the most intriguing places in the solar system. Titan, Saturn's largest moon, had long been a mystery. Even the Voyager probes, which flew past it in the early 1980s, were unable to see through its thick, hazy atmosphere. Cassini, along with its lander, Huygens, finally provided the first detailed look at Titan's surface. What the mission found was unlike anything else in the solar system. Titan has an atmosphere thicker than Earth's, composed mostly of nitrogen, with traces of methane and other organic compounds. This makes it the only moon known to have a dense atmosphere, and the presence of methane in such large quantities raised new questions about how it could be replenished. Cassini's radar and infrared instruments pierced through Titan's orange clouds, revealing a world covered in lakes and rivers. But instead of water, these liquid bodies were filled with methane and ethane. Some lakes were small, scattered across the landscape, while others stretched for hundreds of miles, resembling seas. These discoveries confirmed that Titan had an active weather cycle similar to Earth's, with methane evaporating from the surface, forming clouds, and falling back as rain. This cycle, driven by an unfamiliar chemistry, showed that Titan's surface was constantly reshaped by processes that, while different from those on Earth, were still eerily familiar. Huygens, which landed on Titan in 2005, provided the first close-up images of the moon's terrain. It touched down on a landscape of rounded pebbles, likely made of water ice as hard as rock in Titan's frigid conditions. The lander's instruments detected signs of past rainfall and even evidence of erosion, hinting at a world that, despite its cold temperatures, was shaped by processes similar to those on our own planet. The mission also found complex organic molecules in the atmosphere, raising new questions about whether the chemical building blocks of life could exist in Titan's unique environment. Beneath Titan's surface, Cassini's data suggested the presence of an underground ocean, likely composed of water and ammonia. This subsurface ocean, hidden beneath miles of ice, added another layer of intrigue to Titan. Scientists had already considered the possibility of life forming in Titan's methane-rich lakes, but the potential for an ocean underneath its surface opened up entirely new possibilities. While Titan presented an exotic world covered in organic chemistry, Enceladus offered something even more unexpected: direct evidence of liquid water spraying into space. Cassini first detected hints of this in 2005 when it observed strange plumes erupting from Enceladus's south pole. These plumes, composed of water vapor and ice particles, were blasting out of fissures in the moon's icy crust, reaching hundreds of miles into space. The discovery was groundbreaking. As Cassini flew through these plumes, it gathered data that revealed not just water, but organic molecules and even hydrogen gas. The presence of hydrogen was particularly exciting because it suggested the possibility of hydrothermal vents on the ocean floor. Enceladus's plumes also provided a rare opportunity to study an ocean without having to drill through miles of ice. Cassini was able to fly through the jets and directly sample their composition, giving scientists insights into what might exist beneath the moon's crust. The fact that the plumes contained complex organic molecules, some of the basic ingredients for life, only deepened the mystery. Before Cassini, the search for life beyond Earth had largely focused on planets, with Mars being one of the primary targets. But Enceladus showed that even small, icy moons could host environments where life might be possible. It also raised new questions about how common such moons might be throughout the universe. Cassini's observations of Enceladus confirmed that liquid water could exist in places far from the Sun, kept warm not by solar heat, but by the internal forces of the moon itself. The gravitational pull from Saturn, constantly stretching and flexing Enceladus, generated enough heat to keep its underground ocean from freezing. NASA and other space agencies have since proposed missions designed to return to these moons, with new spacecraft capable of sampling Titan's lakes or flying directly through Enceladus's plumes to search for signs of life. These moons, once considered just small, frozen satellites, had now become some of the most important places in the search for habitable environments beyond Earth. Cassini's mission ended in 2017 when the spacecraft was deliberately sent into Saturn's atmosphere to prevent any chance of contaminating moons like Enceladus or Titan with earthly microbes. But its discoveries continue to influence space exploration today. The data it sent back provided a foundation for future missions, inspiring new efforts and expanding the possibilities of where we might one day find evidence of alien biology. New horizons to Pluto, a radical reimagining of a dwarf planet. Classified as the 9th planet until its controversial redefinition as a dwarf planet in 2006, Pluto was little more than a blurry dot in telescope images. Everything changed in 2015 when NASA's New Horizons spacecraft completed its historic flyby, capturing the first detailed images of Pluto's surface and revealing an incredibly complex world. New Horizons traveled over 4.8 billion kilometers in nearly a decade to reach Pluto, moving faster than any spacecraft prior to it. Because of the vast distance, communication with the spacecraft took hours, making every piece of data precious. The mission's goal was simple: to take a closer look at Pluto and its largest moon, Charon. As New Horizons approached, it sent back the first clear images of Pluto's surface. One of the most striking features was a massive heart-shaped plain now known as Sputnik Planitia. Unlike the cratered landscapes common on most small planetary bodies, this area was surprisingly smooth, suggesting that Pluto's surface was geologically active. The vast nitrogen ice plain appeared to be reshaped by internal processes, with polygonal patterns hinting at slow-moving convection currents beneath the surface. This was unexpected. Most scientists assumed that Pluto, being so far from the Sun, would be a frozen, unchanging world. Beyond Sputnik Planitia, Pluto's surface was covered in towering ice mountains, some reaching over 6,000 meters high. These mountains were not made of rock, but of solid water ice, which in Pluto's frigid temperatures acts much like rock does on Earth. The presence of such large and sharp peaks indicated that Pluto's crust is composed of water ice strong enough to support these massive structures. Another surprise came in the form of haze layers in Pluto's thin atmosphere. New Horizons captured breathtaking images of sunlight scattering through these layers, revealing a complex atmosphere composed mainly of nitrogen, with traces of methane and carbon monoxide. The haze extended far higher than expected, forming delicate blue layers that gave Pluto an otherworldly glow. The discovery of atmospheric haze suggested active chemical processes, possibly involving seasonal changes, as Pluto's highly elliptical orbit takes it closer and farther from the Sun over time. Charon also revealed unexpected geological activity. Instead of a bland crater-covered surface, Charon had deep chasms and massive cliffs, some taller than the Grand Canyon. A vast dark region near its north pole, informally named Mordor Macula, hinted at unique surface processes that could be linked to ice deposits or past cryovolcanic activity. Charon's surface appeared to have been reshaped by internal forces, suggesting that it may have once had a subsurface ocean that later froze and expanded, cracking the surface in the process. New Horizons also provided the first detailed measurements of Pluto's other much smaller moons, Styx, Nix, Kerberos, and Hydra. These moons, spinning chaotically in unpredictable rotations, hinted at a complex history of interactions between Pluto and Charon. Unlike the orderly moons around the gas giants, Pluto's smaller moons tumbled unpredictably, likely influenced by Charon's gravitational pull. Before the flyby, many scientists believed that geological activity required a large, hot interior, like those found in planets such as Earth or Jupiter's moon Io. Pluto challenged that assumption. Despite being far from the Sun and having no strong tidal forces to generate heat, it showed signs of ongoing surface renewal. This raised new questions about the internal processes that could be at work in other distant objects in the Kuiper Belt, where Pluto resides. The mission also reignited discussions about planetary classification. Pluto, with its diverse terrain, active surface and complex atmosphere, defied expectations for a dwarf planet. Some scientists argued that it met the criteria for planethood, regardless of its size. The debate continues, but one thing became clear. Pluto was far from being a dull, frozen rock. Pluto's shifting landscape, the story of icy mysteries and dynamic change. Pluto's surface is a world in motion, shaped by geological and atmospheric processes that continue to reshape its surface over time. One of the most striking indicators of this change is Sputnik Planitia. Its surface is marked by polygonal patterns, and beneath the surface, slow-moving currents carry material upward in some areas and downward in others, erasing old impact craters and creating a constantly shifting terrain. This process resembles the way molten rock circulates beneath the Earth's crust. But on Pluto, it happens with frozen nitrogen instead of liquid magma. On Earth, plate tectonics and volcanic activity are driven by heat from radioactive decay in the planet's core. Pluto, being much smaller and farther from the Sun, lacks this internal heat source. Instead, scientists believe that the slow freezing of a possible underground ocean and the gradual release of energy from nitrogen ice might be driving the changes on the surface. Another sign of Pluto's evolving landscape is the presence of glaciers that appear to flow across the surface. While glaciers on Earth are made of water ice, the ones on Pluto are composed of frozen nitrogen. The nitrogen ice moves across the landscape, carrying material from higher elevations into Sputnik Planitia. Some regions show evidence of ancient glacier-like flows that have solidified into place, while others suggest that the process is still active today. New horizons also revealed a variety of pits and depressions across Pluto's surface, some of which appear to be connected to processes involving the sublimation of ice. Sublimation occurs when a solid turns directly into a gas, skipping the liquid phase. On Pluto, nitrogen and methane ice can sublimate when exposed to sunlight, gradually reshaping the terrain over long periods. Some of the irregularly shaped pits seen by New Horizons resemble those formed by sublimation on other icy bodies, suggesting that Pluto's surface is not just shifting, but actively eroding in response to seasonal changes. Pluto's atmosphere is extremely thin and composed mainly of nitrogen, with traces of methane and carbon monoxide. Despite its low pressure, this atmosphere undergoes significant changes as Pluto moves along its long elliptical orbit around the Sun. As Pluto drifts closer to the Sun, surface ices warm slightly and release gases into the atmosphere. When Pluto moves farther away, the opposite occurs. Gases freeze back onto the surface, forming new ice deposits. This process of atmospheric breathing is believed to drive many of the seasonal changes seen on Pluto's surface. Some areas become covered with fresh ice deposits over time, while others are gradually stripped away. These shifts are not as rapid as the seasons on Earth, but occur over the course of Pluto's 248-year orbit around the Sun. Because New Horizons only observed Pluto during a brief moment in its long journey, scientists must rely on models and past observations to piece together the full picture of its evolving climate. One of the most mysterious features of Pluto's surface is the presence of dark, reddish-colored patches that appear in certain regions, including the equatorial dune fields and the dark terrain of Cthulhu Macula. These dark patches are thought to be made of complex organic molecules called tholins, which form when ultraviolet light from the Sun interacts with methane in Pluto's atmosphere. Over time, these organic compounds settle onto the surface, changing the color and composition of the terrain. The distribution of these dark materials suggests that Pluto's surface chemistry is constantly changing, influenced by both atmospheric and geological processes. The discoveries from the New Horizons mission suggest that Pluto is not an isolated case. Many other objects in the Kuiper Belt could also be active and evolving in ways we have yet to understand. Future missions to this distant region of the solar system may reveal even more surprises, further challenging the idea that small, icy worlds are frozen in time. Beyond Pluto, the hidden wonders of the Kuiper Belt. Beyond Pluto lies a vast and mysterious region of the solar system known as the Kuiper Belt. It is a realm of icy bodies and ancient remnants from the early days of planetary formation. For centuries, astronomers suspected that something existed beyond Neptune, but it wasn't until the late 20th century that telescopes began revealing a population of objects orbiting the Sun in this distant region. The discoveries changed our understanding of the outer solar system and raised new questions about what lies in the cold darkness beyond Pluto. The Kuiper Belt is home to countless icy objects, some as small as a few kilometers across, while others rival Pluto in size. These objects, known as Kuiper Belt objects, or KBOs, orbit the Sun in a broad flattened disk that stretches billions of kilometers into space. Unlike planets, which clear their orbits of debris, KBOs are scattered across a vast area, moving in different paths that hint at past gravitational interactions with Neptune and other giant planets. Scientists believe these objects hold clues to the formation of the solar system, as they are thought to be made of the same primordial material that existed when the planets were forming more than 4 billion years ago. One of the biggest surprises from the New Horizons mission came after its flyby of Pluto, when it continued deeper into the Kuiper Belt and encountered a small ancient object named Arakoth. Unlike Pluto, which has a complex and evolving surface, Arakoth appears to be largely unchanged since the early solar system. Its surface is smooth, reddish, and covered in frozen methane, suggesting it has remained cold and undisturbed for billions of years. The shape of Arakoth, two lobes fused together, suggests it formed gently in the quiet environment of the early Kuiper Belt, rather than experiencing violent collisions like many asteroids in the inner solar system. This discovery provided key insights into how planetesimals, the building blocks of planets, originally formed. Arakoth is just one example of the diversity found in the Kuiper Belt. Many KBOs follow unusual orbits, some of which suggest they were influenced by the movement of Neptune long ago. Others, like Sedna, have highly elongated orbits that take them far beyond the traditional boundaries of the Kuiper Belt, raising questions about whether there might be additional unseen planets lurking in the distant solar system. Some scientists believe that a large, undiscovered world, often referred to as Planet 9, could be hiding far beyond Pluto, shaping the orbits of these distant objects. The Kuiper Belt is also home to other dwarf planets similar to Pluto. Eris, one of the largest known KBOs, was discovered in 2005 and is nearly the same size as Pluto. Its discovery played a major role in the reclassification of Pluto as a dwarf planet, as astronomers realized that Pluto was not unique, but rather one of many large bodies in this distant region. Eris has a highly reflective surface, covered in a layer of frozen methane and nitrogen, and it follows an orbit that takes it much farther from the Sun than Pluto. Another dwarf planet, Makemake, is slightly smaller than Pluto and has a surface covered in methane ice. It lacks a significant atmosphere. Some KBOs show signs of unusual activity. Haumea, another large object in the Kuiper Belt, spins at an incredibly fast rate, completing one full rotation in less than 4 hours. This rapid spin has stretched Haumea into an elongated shape, making it one of the most unusual large bodies in the solar system. Haumea is also surrounded by a ring of material, making it the only known KBO with such a feature. This discovery suggests that collisions between Kuiper Belt objects may have been common in the past, scattering debris that eventually formed rings or moons around some of these distant worlds. Many of KBOs contain a mixture of water ice, methane, and other frozen compounds that have remained largely unchanged since the formation of the solar system. By studying their surfaces and orbits, scientists can piece together a timeline of how the giant planets moved and interacted with the surrounding material billions of years ago. Some theories suggest that Neptune may have migrated outward over time, scattering KBOs into their current orbits and shaping the structure of the Kuiper Belt as we see it today. The Kuiper Belt extends far beyond what telescopes can easily observe, and many of its objects are too small and faint to detect from Earth. New Horizons provided a rare glimpse into this distant world, but future missions will be needed to explore it further. Some scientists have proposed sending another spacecraft deeper into the Kuiper Belt, possibly to visit multiple objects and study their compositions up close. Others suggest that powerful next-generation telescopes, such as the James Webb Space Telescope, or JWST, and its successors, may help identify more KBOs and refine our understanding of their properties. Beyond the Kuiper Belt, the solar system fades into an even more mysterious region known as the Oort cloud. While the Kuiper Belt consists of relatively flat, disc-shaped orbits, the Oort cloud is thought to be a vast spherical shell of icy bodies that surrounds the entire solar system. These objects are too distant to observe directly, but their existence is inferred from the behavior of long-period comets that occasionally fall into the inner solar system. Some of these comets may have originated in the Kuiper Belt before being ejected into wider orbits by gravitational interactions with Neptune or other planets. Voyager's bold legacy, breaking the boundaries of our solar system. The Voyager missions began as an ambitious plan to explore the outer planets, but they evolved into something far greater, a journey beyond the solar system itself. Launched in 1977, Voyager 1 and Voyager 2 were designed to take advantage of a rare planetary alignment that occurs only once every 176 years. This alignment allowed them to use gravitational assists to travel from one planet to the next, dramatically increasing their speed and extending their lifespans. What started as a mission to explore Jupiter and Saturn soon became a grand tour of the outer planets, and eventually an escape from the Sun's influence altogether. Voyager 1 was the first to reach interstellar space, officially crossing the boundary of the heliosphere in 2012. The heliosphere is the vast bubble of charged particles and magnetic fields created by the Sun's solar wind, and its outer edge marks the point where the Sun's influence gives way to the forces of interstellar space. Voyager 2 followed suit in 2018, providing another valuable data point for understanding this transition. Both spacecraft continued to send back measurements of cosmic rays, magnetic fields, and the density of the surrounding medium, giving scientists their first direct glimpse of what lies beyond the solar system. Before reaching this distant frontier, the Voyager probes provided humanity with its first up-close look at the gas giants and their moons. Voyager 1's encounter with Jupiter in 1979 revealed the planet's turbulent atmosphere in detail, capturing images of the Great Red Spot, a centuries-old storm that continues to rage across the planet's surface. The spacecraft also made the groundbreaking discovery that Io was geologically active. This unexpected finding reshaped ideas about how moons could generate heat through tidal interactions with their host planets. Voyager 2 took a different route, allowing it to visit all four of the outer planets: Jupiter, Saturn, Uranus, and Neptune. At Saturn, it provided stunning images of the planet's intricate ring system, showing how its rings were made up of countless individual particles that formed complex patterns. The spacecraft also encountered Titan. Titan's dense haze prevented visible light cameras from seeing the surface, but its presence suggested an active world beneath the clouds. Uranus was a mystery before Voyager 2 arrived in 1986. Unlike the gas giants, which had dynamic swirling atmospheres, Uranus appeared as a nearly featureless blue-green sphere. However, the spacecraft discovered that the planet's magnetic field was tilted at an extreme angle, possibly due to a massive impact in its past. Voyager 2 also found evidence of rings around Uranus, similar to those at Saturn, but far more subtle and difficult to detect. The probe's flyby of Neptune in 1989 was equally revealing. Neptune's atmosphere was found to be far more active than Uranus's, with the fastest winds ever recorded in the solar system. The spacecraft also discovered the Great Dark Spot, a massive storm similar to Jupiter's Great Red Spot, though it later disappeared when observed by the Hubble Space Telescope in the following years. Perhaps the most iconic moment of the Voyager missions came in 1990, when Voyager 1 turned its camera back toward Earth and captured the famous pale blue dot image. From a distance of 3.7 billion miles, Earth appeared as a tiny speck, barely visible against the vastness of space. The image, along with astronomer Carl Sagan's reflections on it, became a powerful symbol of humanity's small place in the cosmos. As the Voyagers left the planets behind, they continued their mission as interstellar explorers. Their instruments, designed for planetary science, were now repurposed to study the edge of the heliosphere and the transition into interstellar space. The heliopause, the boundary where the solar wind slows and merges with the interstellar medium, had long been theorized but never directly measured. When Voyager 1 crossed into interstellar space, scientists confirmed that the density of surrounding particles had increased, indicating it had left the solar wind's domain. Voyager 2 provided a second set of observations, confirming that the transition region was more complex than previously thought, with shifting boundaries influenced by solar activity. Even after more than 4 decades, the Voyager probes continue to send back data, though their power is fading. Their radio signals take over 20 hours to reach Earth, traveling at the speed of light. To conserve energy, NASA has gradually shut down non-essential systems, prioritizing instruments that can still provide valuable scientific data. Despite their weakening power supplies, the spacecraft remain humanity's farthest-reaching emissaries, continuing to drift through space, carrying with them the golden records, messages from Earth intended for any extraterrestrial civilization that might one day encounter them. The golden records, placed aboard both Voyager 1 and Voyager 2, were a unique addition to the mission. Conceived by a team led by Carl Sagan, the records contain a collection of sounds, images, and greetings in multiple languages designed to represent the diversity of life and culture on Earth. They include everything from whale songs and thunderstorms to music by Beethoven and Chuck Berry. The records serve as a time capsule, a snapshot of human civilization preserved in the cold vacuum of space. While the chances of them ever being found are slim, they symbolize a hopeful message, a declaration that humanity once existed and reached beyond its home world. They are expected to keep transmitting until at least the 2030s, after which they will fall silent. But their journey will not end. They will continue moving through interstellar space, untouched and unchanged for millions of years, carrying with them the story of a species that once looked up at the stars and dared to explore. Crossing the heliospheric edge, first glimpses of interstellar space. The Sun constantly emits a stream of solar wind. These particles create a bubble around the solar system, which is the heliosphere. The edge of this bubble is called the heliopause, where the solar wind slows and eventually stops pushing outward against interstellar space. Beyond this boundary, the influence of the Sun weakens, and the particles that exist there come from other stars, shaped by galactic forces rather than our own star's activity. When Voyager 1 crossed into interstellar space, scientists knew something extraordinary had happened. Instruments on board detected a sudden increase in the number of high-energy particles from beyond the solar system. At the same time, particles from the Sun's solar wind all but disappeared. The spacecraft also measured a change in the surrounding magnetic field, showing that it was now aligned with the broader galaxy rather than the Sun's influence. These shifts were evidence that Voyager 1 had finally exited the heliosphere, becoming the first human-made object to enter the space between the stars. Voyager 2, which took a different path, crossed the heliopause 6 years later. The readings it sent back confirmed that the boundary of the solar system is not uniform. It varies depending on solar activity, with the shape of the heliosphere expanding and contracting like a balloon as the Sun's energy output changes. This discovery showed that our solar system's edge is not a strict border, but a dynamic region that shifts over time. The space beyond the heliosphere is not empty. Instead, it is filled with a thin mixture of gas and dust known as the interstellar medium. This material is what remains from ancient stars that lived and died long before our solar system was born. Scientists had long wondered how the solar wind interacts with this medium, and Voyager's data provided the first direct evidence. The spacecraft found that the interstellar medium is denser than expected, with charged particles behaving differently than those inside the heliosphere. This confirmed that the space between stars is not a void, but an active environment shaped by the remnants of past stellar generations. One of the surprises from Voyager's journey was the discovery of pressure waves traveling through interstellar space. These waves are created when the Sun experiences coronal mass ejections, sending bursts of energy outward. Even though these eruptions start near the Sun, they continue traveling outward until they eventually push against the interstellar medium. Voyager's instruments recorded these waves as they moved through space, providing valuable information on how energy from the Sun extends far beyond the planets. The region just beyond the heliopause also turned out to be more complex than expected. Instead of a smooth transition, Voyager found a turbulent zone where interstellar particles and solar particles mix. Scientists had theorized that the boundary between the solar system and interstellar space would be a gradual change, but Voyager's data showed unexpected variations in density and magnetic fields. The interstellar medium contains the raw materials that form stars and planets, including essential elements like carbon, oxygen, and nitrogen. By studying this region directly, scientists can learn more about how new planetary systems emerge from the remains of older stars. Understanding the conditions of interstellar space also helps in planning for future missions that may one day travel beyond our solar system, whether robotic probes or, in the distant future, crewed spacecraft. As the Voyagers move farther, their instruments are detecting fewer particles from the Sun and more from interstellar sources. These measurements are helping scientists refine their models of how the heliosphere interacts with the broader galaxy. Eventually, as the spacecraft drift even farther away, they will enter a region where the Sun's influence is almost non-existent, offering an even purer look at the interstellar medium. The heliosphere itself is shaped by forces beyond our solar system. Scientists now believe that the Sun is traveling through a denser region of interstellar space than it did in the past. This could affect the size and shape of the heliosphere, changing how it protects the solar system from incoming cosmic rays. Voyager's measurements will help determine whether this region of space has influenced Earth's climate or conditions in the past, providing new insights into how the solar system interacts with the galaxy as a whole. One question that remains open is how long the influence of the Sun extends. Even though the spacecraft is beyond the heliosphere, the Sun's gravity still holds sway over the outermost comets in the Oort cloud. Voyager will take thousands of years to reach the true boundary of the solar system, the point where the Sun's gravitational influence fades completely. Cosmic rays and magnetic currents navigating uncharted territories. Cosmic rays are among the most energetic particles in the universe, traveling through space at nearly the speed of light. They come from a variety of sources, including distant supernova explosions, the remnants of massive stellar deaths, and possibly even more exotic origins like black holes and neutron star collisions. For decades, these particles remained largely mysterious, detected indirectly as they crashed into Earth's atmosphere. But as the Voyager spacecraft moved beyond the solar system, they provided an unprecedented opportunity to study cosmic rays in an environment untouched by Earth's magnetic field. One of the first major findings was the sudden increase in the number of cosmic rays detected after Voyager 1 crossed the heliopause. This confirmed that the solar system, like an island in a vast cosmic ocean, is partially insulated from the harsher radiation that fills the galaxy. While the heliosphere does block some of these particles, it does not do so uniformly. Instead, cosmic rays are influenced by the complex structure of the Sun's magnetic field, which twists and changes as the Sun rotates. Voyager's instruments revealed that some cosmic rays manage to penetrate the heliosphere, even from great distances, slipping through weak spots in the Sun's magnetic defenses. This has major implications for understanding the radiation environment that future deep space travelers might encounter. The data collected by Voyager also shed light on how cosmic rays are distributed. Instead of a smooth and even spread, they seem to travel in waves and clusters. Scientists suspect that this is due to the influence of magnetic fields, which guide and redirect the paths of these charged particles. When cosmic rays encounter a magnetic field, they do not travel in straight lines, but spiral along the field's direction. This creates patterns that scientists are trying to decipher. Scientists had expected that, once beyond the heliopause, Voyager would detect a magnetic environment significantly different from the Sun's. However, the spacecraft found that the magnetic field in interstellar space was still closely aligned with the Sun's field. Instead of a sharp boundary where the solar and interstellar fields separate, the two seem to be connected in unexpected ways, possibly through magnetic reconnection, an event where magnetic field lines break and rejoin, releasing energy. These observations have helped refine theories about how magnetic fields shape the universe. Magnetic fields are invisible, but they play a fundamental role in guiding the movement of cosmic rays, influencing the formation of stars, and even affecting the structure of galaxies. Without magnetic fields, cosmic rays would travel in straight paths, meaning they would be far more destructive to planets and other objects in space. The fact that magnetic fields twist and bend cosmic rays helps diffuse their energy, preventing localized radiation damage and spreading their effects more evenly across space. Voyager's findings also provided new insight into the cosmic ray sea, the ever-present background radiation that fills interstellar space. By measuring the energy levels and sources of these cosmic rays, scientists are learning more about the violent events that create them. Some cosmic rays detected by Voyager appear to have originated from recent supernovae within our galactic neighborhood, hinting at past explosions that may have influenced the formation of nearby star systems, including our own. In addition to the Sun's influence, Voyager has also detected signs of distant shock waves originating from much larger-scale cosmic events. These might include supernova shock waves propagating through the interstellar medium, or disturbances created by the movement of entire star systems. One of the long-term goals of studying cosmic rays and magnetic fields is to improve space travel safety. High-energy cosmic rays can damage human DNA and increase cancer risks. The data from Voyager is helping scientists understand how cosmic rays behave in deep space, which could lead to better shielding strategies for future missions beyond Earth's protective atmosphere. If humans are ever to venture beyond the Moon and Mars, understanding how to mitigate cosmic ray exposure will be essential. Beyond human exploration, cosmic rays may also hold clues about the fundamental nature of the universe. Some of the highest energy cosmic rays detected have energies far beyond what current particle accelerators on Earth can produce. These ultra-high energy particles may originate from some of the most extreme environments in the universe, such as the vicinity of black holes or the remnants of hypernovae. Studying them could offer insights into physics beyond what is currently known. The interstellar medium, once thought to be a featureless void, is now recognized as a dynamic and structured environment, filled with interactions that affect everything from planetary systems to the formation of stars. Cosmic rays, once considered little more than high-energy nuisances, are now seen as essential tracers of cosmic events, providing evidence of the universe's most powerful explosions and forces. The magnetic fields that shape their paths, once barely detectable, are now being mapped in greater detail, revealing a hidden structure that connects different regions of space. Gravitational interactions in deep space. Gravity is the invisible architect of the universe, guiding the movement of planets, stars, and galaxies. Every object in space, from the smallest asteroid to the most massive black hole, exerts a gravitational pull on everything around it. The careful balance of these gravitational influences determines everything from the stability of planetary systems to the formation of entire galaxies. Earth and its neighboring planets follow elliptical orbits around the Sun, a motion first described by Johannes Kepler in the 17th century. Kepler's laws of planetary motion, later confirmed by Isaac Newton's theory of gravitation, revealed that these orbits are the result of a constant gravitational tug-of-war. The Sun's massive gravitational pull tries to draw the planets inward, but their forward motion keeps them in orbit. This balance creates the orderly paths that planets follow as they move through space. When two planets or moons pass close to each other, their gravitational forces interact, sometimes subtly shifting their orbits. These gravitational encounters can be temporary, causing slight changes in speed or direction, or they can be dramatic, leading to long-term shifts in an object's trajectory. In some cases, these interactions can even eject objects from their original systems, sending them into deep space as rogue planets or interstellar asteroids. One of the most fascinating examples of gravitational interactions is the phenomenon of orbital resonance. This occurs when two or more celestial bodies exert regular gravitational influences on each other, causing them to maintain a stable pattern over time. A well-known example of this can be seen in Jupiter's moons, particularly Io, Europa, and Ganymede. These moons are locked in a precise resonance, where for every 4 orbits Io completes, Europa completes exactly 2, and Ganymede completes exactly 1. This gravitational synchronization helps maintain their orbits. Similar resonances can be found in planetary ring systems. Saturn's rings are shaped by the gravitational pull of its moons. Some of Saturn's smaller moons act as shepherds, keeping the rings in place through their gravitational influence. Others create gaps within the rings, clearing out regions where their gravity prevents ring particles from settling. In binary star systems, where 2 stars orbit a common center of mass, their gravitational pull keeps them bound together. Some binary systems consist of stars that are nearly identical in mass, orbiting each other in a relatively stable dance. Others have a more extreme relationship, where a massive star's gravity pulls material away from its smaller companion. This process can lead to the formation of accretion disks, where stolen material spirals around the larger star or even falls into a black hole. Within a galaxy, stars orbit its center, influenced by the gravitational pull of both visible matter and the unseen presence of dark matter. The rotation of galaxies was one of the first major clues that dark matter exists, as astronomers observed that galaxies were spinning faster than they should be based on their visible mass alone. The only explanation was that an invisible form of mass, later termed dark matter, was contributing additional gravitational pull. Spacecraft traveling through the solar system rely on gravity assists, or gravitational slingshots, to gain speed and adjust their trajectories. By flying close to a planet, a spacecraft can use the planet's gravity to accelerate and change direction without using additional fuel. This technique has been used by missions like Voyager, Cassini, and New Horizons to reach distant targets that would otherwise require far more energy to explore. The evolution of spacecraft instrumentation. Space exploration has always depended on the tools sent beyond Earth's atmosphere. From the earliest satellites to the most advanced probes, the evolution of spacecraft instrumentation has determined what questions can be answered and what mysteries remain unsolved. Each new generation of instruments refines the search, offering a clearer picture of distant worlds, deep space phenomena, and even the fundamental nature of the universe itself. The story of space exploration is, in many ways, the story of how these instruments have advanced, allowing humanity to extend its senses far beyond what was once imaginable. The first space instruments were designed with a simple goal: survival. The early satellites of the 1950s and 1960s, including Sputnik and Explorer 1, carried basic sensors to detect radio signals, measure temperature, and observe changes in Earth's magnetic field. These tools provided a first glimpse into conditions beyond the atmosphere, but their capabilities were limited. Instruments had to be small, lightweight, and capable of functioning without human intervention. Telemetry systems, which allowed satellites to send data back to Earth, were also in their infancy. The signals carried by these early spacecraft were often weak, requiring large ground-based antennas to capture and decode them. As space agencies gained experience, spacecraft instrumentation became more sophisticated. The Pioneer and Mariner programs of the 1960s and 1970s marked the first attempts to explore other planets. These missions carried cameras, spectrometers, and magnetometers, all designed to operate in extreme conditions. The cameras, while rudimentary by today's standards, provided the first close-up images of other worlds. Spectrometers, which analyze light to determine the composition of surfaces and atmospheres, revealed the presence of unexpected chemicals on planets like Mars and Venus. Magnetometers mapped planetary magnetic fields, uncovering details about internal structures hidden beneath thick atmospheres or icy crusts. The development of digital imaging revolutionized spacecraft instrumentation in the late 20th century. The Viking landers, which touched down on Mars in the 1970s, carried the first high-resolution cameras capable of capturing detailed surface images. These cameras used digital sensors instead of film, allowing images to be transmitted directly to Earth without physical retrieval. This advance laid the foundation for modern planetary exploration, enabling future spacecraft to capture stunning images of distant worlds without the need for human handling. Another key innovation came with the miniaturization of electronics. Early spacecraft relied on bulky, power-hungry components, limiting how many instruments could be included in a mission. As technology improved, smaller, more efficient instruments became possible. The Galileo spacecraft, which studied Jupiter in the 1990s, carried a suite of compact instruments capable of measuring radiation, temperature, and atmospheric composition with unprecedented precision. This ability to carry multiple sensors on a single probe allowed for a more complete understanding of planetary environments. Early probes required constant oversight from ground control, with engineers making real-time adjustments to their instruments. Modern spacecraft, however, have onboard computers that can make decisions autonomously. The Mars rovers, beginning with Sojourner in 1997 and continuing with Spirit, Opportunity, Curiosity, and Perseverance, are equipped with navigation and analysis tools. These allow them to identify interesting geological features, select targets for study, and adjust their scientific priorities based on real-time data. Another major advancement has been the ability to collect and analyze physical samples remotely. The OSIRIS-REx mission, launched in 2016, successfully retrieved samples from the asteroid Bennu using a robotic arm equipped with multiple instruments. Unlike earlier missions that relied solely on remote sensing, this spacecraft was able to bring material back to Earth for detailed laboratory study. The upcoming Artemis program, aimed at returning humans to the Moon, will build upon this approach by using robotic instruments to identify promising sites for sample collection before astronauts arrive. In the early days of space exploration, data transmission rates were slow, limiting how much information could be sent back to Earth. The Deep Space Network, a global system of large radio antennas, has played a critical role in improving communication with distant spacecraft. Advances in radio signal processing have allowed spacecraft to send back higher resolution images, more detailed spectroscopic readings, and even real-time data streams from landers and rovers. The introduction of laser communication systems, currently being tested in some missions, promises to further increase data transmission speeds, allowing for even more complex scientific instruments in future probes. The ability to detect and analyze invisible wavelengths of light has been another turning point. Traditional cameras capture visible light, but many of the most important discoveries in space come from observing other parts of the electromagnetic spectrum. Infrared telescopes, like those aboard the Spitzer Space Telescope and the JWST, can see through dust clouds to reveal star-forming regions and exoplanet atmospheres. Ultraviolet and X-ray instruments, such as those on the Chandra X-ray Observatory, provide insights into high-energy cosmic events, including black hole activity and supernova remnants. The ability to observe space in multiple wavelengths has transformed the understanding of how galaxies, stars, and planetary systems evolve. Gravitational wave detectors, such as LIGO, measure tiny distortions in space-time caused by distant cosmic collisions. These observations complement traditional telescopes by providing a new way to study extreme cosmic events. Space-based neutrino detectors, still in their early stages, aim to detect ghostly particles that pass through matter almost undisturbed, offering clues about the most energetic processes in the universe. The push toward miniaturization continues with the rise of CubeSats, small modular satellites that can be deployed in large numbers. These tiny spacecraft carry miniature versions of traditional instruments, allowing for low-cost, high-frequency observations of space environments. Some CubeSats have been designed to accompany larger missions, providing additional perspectives on planetary bodies or relaying data from difficult-to-reach regions. The Mars Cube 1 mission, for example, consisted of 2 small CubeSats that relayed signals from the InSight lander as it descended onto the Martian surface. Quantum sensors, which rely on the principles of quantum mechanics to detect tiny changes in gravity and magnetic fields, are being developed for future missions. These could allow spacecraft to map underground structures on planets and moons with unprecedented detail. Self-repairing materials and nanotechnology-based instruments may also play a role, enabling spacecraft to withstand extreme conditions and extend their operational lifetimes. Every advancement in sensors, cameras, spectrometers, and communication tools expands the reach of exploration. As these technologies continue to evolve, the ability to probe deeper into space and uncover new phenomena will only grow, bringing humankind closer to answering some of the most fundamental questions about the universe. Molecular mysteries, tracing the origins of life beyond Earth. The search for life beyond Earth has always been a driving force in space exploration. While telescopes and planetary probes capture breathtaking images of distant worlds, their most crucial work often happens on a molecular level. The building blocks of life, such as amino acids, organic molecules, and complex carbon compounds, are scattered throughout the cosmos. Understanding where these molecules form, how they interact, and whether they could lead to life is one of the great scientific challenges of our time. Deep space missions, equipped with sophisticated instruments, are unraveling these molecular mysteries, offering glimpses into the chemical foundations that might give rise to living organisms. The search for life's molecular precursors begins with studying the chemistry of the planets and moons in our solar system. Mars has been a key focus for these investigations, with a series of rovers and orbiters examining its surface and atmosphere for organic compounds. The Curiosity rover, using its onboard sample analysis at Mars, or SAM, instrument, detected a variety of organic molecules embedded in Martian rocks. These molecules, though not direct evidence of life, suggest that the building blocks of life existed on Mars billions of years ago. The Perseverance rover, currently exploring Jezero crater, is taking this search further by collecting and storing rock samples that will eventually be analyzed in detail on Earth. Beyond Mars, Saturn's moon Enceladus has emerged as one of the most intriguing places to study molecular signatures. The Cassini spacecraft's close flybys of Enceladus revealed towering plumes of water vapor containing complex organic molecules. The Huygens probe, which landed on Titan in 2005, recorded data suggesting that the moon's methane lakes and nitrogen-rich atmosphere could support the formation of prebiotic chemistry. Some researchers speculate that life could develop on Titan using chemistry that is vastly different from Earth's, possibly relying on liquid methane instead of water. The upcoming Dragonfly mission, set to launch later this decade, will explore Titan's surface and atmosphere in search of further evidence of complex organic processes. Beyond the solar system, space telescopes are also playing a crucial role in tracing molecular signatures. JWST, equipped with powerful infrared instruments, has begun analyzing the atmospheres of exoplanets. By studying how starlight filters through a planet's atmosphere, it can detect chemical signatures of molecules such as water vapor, methane, and carbon dioxide. Some of these molecules are essential for life on Earth, making their presence on distant worlds a tantalizing clue that conditions might be right for biological activity. In some cases, telescopes have even detected biosignature gases like phosphine, a compound associated with microbial life, though the interpretations remain debated. Asteroids and comets have also provided crucial insights into the molecular foundations of life. These ancient space rocks preserve chemical conditions from the early solar system, offering a window into the materials that may have seeded planets with organic compounds. The OSIRIS-REx and Hayabusa 2 missions successfully returned samples from asteroids, allowing scientists to analyze their composition in laboratories on Earth. The discovery of amino acids in these samples supports the idea that the ingredients for life may have arrived on Earth from space. Cometary missions like Rosetta, which studied the composition of Comet 67P, have also found organic molecules, including complex carbon structures that hint at the early chemistry of the solar system. Radio telescopes have detected complex organic compounds in molecular clouds where new stars and planets form. The ALMA Observatory in Chile has identified molecules like glycolaldehyde, a simple sugar, in star-forming regions light years away. These discoveries suggest that organic chemistry is not unique to our solar system, but is a fundamental process that happens throughout the galaxy. If molecules related to life can form in the cold depths of interstellar space, they may also be present on newly formed planets, increasing the likelihood that life could emerge elsewhere. One of the key challenges in this search is distinguishing between biological and non-biological processes. Many organic molecules can form through natural chemical reactions unrelated to life. On Earth, life has fundamentally altered the composition of the atmosphere and oceans, producing gases like oxygen and methane in ways that would not occur on a lifeless planet. Spacecraft studying other worlds must rely on indirect evidence to determine whether observed molecules are linked to biological activity or simply the result of geochemical reactions. The search for life's molecular origins is an ongoing effort that requires a combination of planetary missions, space telescopes, and laboratory studies on Earth. Whether or not these molecules have led to life elsewhere remains one of the biggest questions in science, but the growing body of evidence suggests that the basic ingredients for life are widespread. The more scientists uncover about these molecular mysteries, the closer they get to answering one of the oldest and most profound questions: whether humanity is alone in the cosmos. Europa Clipper's promise: probing the secrets beneath the ice. The Europa Clipper mission represents one of the most ambitious efforts to explore the possibility of life beyond Earth. Targeting Jupiter's icy moon Europa, the spacecraft will embark on a detailed investigation of the moon's thick ice shell and the vast ocean believed to exist beneath it. This mission is designed to probe the moon's hidden depths, searching for conditions that could support microbial life. The Europa Clipper will be performing multiple flybys of the moon while in orbit around Jupiter. Instead of landing, the spacecraft will make nearly 50 close passes over Europa, collecting data with a suite of advanced instruments. One of its most important tools is an ice-penetrating radar system that will allow scientists to see beneath the surface. By bouncing radio waves off the ice and analyzing the reflected signals, scientists will be able to map the structure of the ice shell and determine its thickness. If there are subsurface lakes or thinner regions of ice, the radar will detect them, providing valuable clues about the ocean below. Another key instrument is the magnetometer, which will measure Europa's magnetic field and provide insights into the depth and salinity of its ocean. Previous data from the Galileo spacecraft suggested that Europa's ocean is electrically conductive, likely due to dissolved salts. By measuring how Jupiter's powerful magnetic field interacts with Europa, the Europa Clipper can help refine estimates of the ocean's composition and depth. If the ocean contains a mix of salts similar to those found in Earth's oceans, it could be even more hospitable to life. The spacecraft will also carry infrared and ultraviolet spectrometers to study the Moon's surface in detail. These instruments will identify the composition of ice and any materials that might have originated from the ocean below. Scientists are particularly interested in regions where surface ice appears disrupted or discolored, as these areas could indicate recent geological activity or upwelling of ocean material. If organic molecules or complex carbon-based compounds are detected in these regions, it would strengthen the case for Europa's potential habitability. Observations from the Hubble Space Telescope and reanalyzed data from Galileo suggest that geyser-like plumes of water vapor may be erupting from the Moon's surface. These plumes could provide a direct link to the ocean below, allowing Europa Clipper to sample ocean material without having to drill through the ice. The spacecraft will be equipped with a mass spectrometer capable of analyzing the chemical composition of these plumes, searching for organic compounds, salts, and other key ingredients. If the plumes contain complex molecules similar to those associated with life on Earth, it would be one of the most significant discoveries in space exploration. Unlike many other icy moons that are heavily cratered, Europa's surface appears relatively young and smooth, with long cracks and ridges stretching across it. This suggests that the ice shell is in motion, possibly undergoing convection as warmer ice from below rises and cooler ice sinks. By studying these surface features in high resolution, the Europa Clipper will help scientists understand how the ice moves and whether it allows for exchanges between the surface and the ocean. If there are areas where ocean material reaches the surface, they could be prime locations for future lander missions. On Earth, deep-sea hydrothermal vents support thriving ecosystems despite the absence of sunlight. Instead of photosynthesis, these environments rely on chemical energy from the interaction of water and rock. The data collected by the Europa Clipper will help scientists assess whether such conditions are possible beneath Europa's ice. If a subsurface ocean on this moon proves to be habitable, it raises the possibility that other icy worlds, such as Enceladus, Ganymede, or even distant moons in the Kuiper Belt, could also harbor life. The study of Europa could reshape our understanding of where life can exist and how common it might be in the universe. JUICE and the future of Jupiter's icy moons exploration. The Jupiter Icy Moons Explorer, or JUICE, represents a major step forward in the exploration of the Jovian system. Developed by the European Space Agency, this mission is designed to study Ganymede, Europa, and Callisto. Unlike previous missions that have only made brief flybys, JUICE will conduct an in-depth comparative study, revealing how these moons interact with Jupiter and how their environments have evolved over time. At the heart of JUICE's mission is Ganymede. Bigger than Mercury, Ganymede is the only moon known to generate its own magnetic field. Scientists believe that beneath its thick crust of ice, Ganymede harbors a vast ocean, possibly containing more water than all of Earth's oceans combined. The JUICE spacecraft will be the first to orbit Ganymede, allowing for an extended investigation into its structure, geology, and internal dynamics. One of the primary objectives is to measure the thickness of Ganymede's ice shell and determine how its ocean interacts with the surrounding layers. Using radar capable of penetrating the ice, JUICE will map the subsurface and identify whether pockets of liquid water exist closer to the surface. The mission will also analyze the moon's thin atmosphere, which contains traces of oxygen, to better understand how it interacts with Jupiter's powerful radiation. JUICE will conduct multiple flybys of Europa, collecting high-resolution images and scanning for evidence of subsurface lakes or areas where liquid water might be accessible. Scientists are particularly interested in how Jupiter's intense radiation affects Europa's surface chemistry, as interactions between radiation and ice can produce complex molecules that could play a role in the development of life. Callisto, the third moon under investigation, is often described as one of the most ancient and heavily cratered objects in the solar system. Unlike Europa or Ganymede, Callisto shows little sign of internal activity, yet it too may have a subsurface ocean. By studying Callisto, JUICE will provide a point of comparison, helping scientists understand why some moons remain geologically active, while others appear frozen in time. Callisto's distance from Jupiter also means it experiences less radiation, which may have preserved its surface chemistry in a more stable state over billions of years. A key aspect of the mission is to investigate how these three moons have evolved within Jupiter's gravitational influence. As the largest planet in the solar system, Jupiter generates powerful tidal forces that stretch and squeeze its moons, driving geological activity. By studying Ganymede, Europa, and Callisto together, JUICE will provide a broader picture of how these forces shape icy worlds. The spacecraft itself is equipped with 10 scientific instruments, including cameras, spectrometers, a laser altimeter, and a magnetometer. These tools will allow JUICE to map surface features in detail, analyze the composition of ice and minerals, and measure variations in gravitational and magnetic fields. The spacecraft will also monitor Jupiter's magnetosphere, studying how charged particles from the planet interact with its moons and how these interactions influence their atmospheres and surfaces. One of the biggest challenges for JUICE is operating in Jupiter's harsh environment. The planet's radiation belts are some of the most intense in the solar system, and while JUICE's primary focus is on Ganymede, it will need to survive multiple flybys of Europa, which sits within a particularly strong radiation zone. The spacecraft is designed with shielding to protect its sensitive instruments, ensuring that it can continue collecting data throughout its mission. JUICE will take a long journey to reach Jupiter. After launching from Earth, the spacecraft will use gravity assists from Venus and Earth to gain momentum, a process that will take nearly 8 years. Once it arrives in the Jovian system, it will spend several years conducting flybys of Europa and Callisto before settling into orbit around Ganymede for its final phase of exploration. By studying multiple moons in one system, JUICE will provide insights that no single target mission could achieve. Scientists will be able to compare how similar worlds respond to different conditions, offering a clearer picture of how icy moons evolve and whether they might support life. Dragonfly's journey, exploring Titan's prebiotic landscapes. Dragonfly, set to be launched in 2028, will explore Titan with a unique mobility that allows it to traverse vast distances and study multiple locations in ways that no previous lander or rover has been able to achieve. Unlike traditional rovers that rely on wheels to navigate the surface, Dragonfly will use a system of rotors, similar to a drone, to fly from one site to another, opening up an unprecedented opportunity to analyze Titan's complex and diverse landscapes. Dragonfly is designed to investigate Titan's chemistry in detail, searching for the building blocks of life and exploring how prebiotic conditions could have developed in an environment vastly different from Earth's. Unlike most celestial bodies studied by spacecraft, Titan has a dense atmosphere. This atmosphere allows Dragonfly to fly with ease, as the combination of low gravity and thick air creates an environment where powered flight is more efficient than on Earth. The rotorcraft is equipped with 8 rotors and can take off and land vertically, enabling it to explore a wide range of terrains. Over the course of its mission, Dragonfly is expected to travel hundreds of kilometers, covering more ground than any previous planetary rover. One of the primary goals of the mission is to analyze the chemical composition of Titan's surface. The Moon's landscape is shaped by lakes and rivers of liquid methane and ethane. These hydrocarbons rain down from the atmosphere, carving channels and valleys into the icy crust. Dragonfly will land in the equatorial region known as the Shangri-La Dune Fields, a vast area covered in sand-like grains composed of organic material. From there, it will conduct a series of flights to various locations, collecting samples and analyzing their composition using advanced onboard instruments. Among these instruments is a mass spectrometer capable of identifying complex organic molecules. Titan is believed to harbor a wide variety of carbon-based compounds, and Dragonfly's ability to detect and study these molecules could provide key insights into prebiotic chemistry, the chemical processes that occur before life emerges. The mission will also examine how these organic materials interact with liquid methane and ethane, which could shed light on the chemical pathways that might lead to the formation of more complex molecules. Titan's thick atmosphere acts as a shield against radiation and cosmic rays, creating a relatively stable environment on the surface. However, methane in the atmosphere undergoes continuous chemical reactions, breaking apart under sunlight and recombining to form an array of organic compounds. Over time, these materials settle onto the surface, accumulating in layers that preserve a record of Titan's chemical history. Dragonfly will study how these atmospheric processes contribute to the formation of surface features and determine whether similar mechanisms may have played a role in shaping the conditions for life on early Earth. In addition to investigating the surface, Dragonfly will also search for signs of subsurface activity. Some models suggest that Titan may have a liquid water ocean beneath its icy crust, similar to other moons in the outer solar system. While Dragonfly is not equipped to drill into the ice, it will examine the terrain for clues that might indicate interactions between the surface and a deeper liquid layer. If materials from the subsurface have been brought up by impact craters or cryovolcanic activity, Dragonfly's instruments will be able to analyze their composition. Dragonfly's mobility allows it to explore multiple sites with different geological histories, providing a broader understanding of Titan's evolution. One of the most significant locations it will visit is the Selk Impact Crater, a region where liquid water and organic molecules may have mixed in the past. Impact events on Titan can create temporary liquid water environments by melting the icy crust, and Selk Crater presents an opportunity to study whether such interactions could have led to the formation of complex chemical structures. Another advantage of Dragonfly's flight capability is its ability to land, analyze, and then relocate. Unlike rovers that must carefully navigate obstacles on the ground, Dragonfly can simply lift off and fly to a new area if an interesting feature is spotted in the distance. This flexibility ensures that the mission can adapt to new discoveries and make the most of its time on Titan. Communication between Dragonfly and Earth presents a challenge due to Titan's distance from our planet. The spacecraft will rely on relays through the Deep Space Network, sending back data at regular intervals. Because of the communication delay, Dragonfly will operate autonomously, using onboard systems to navigate and make real-time decisions about its flight paths and scientific observations. The success of Dragonfly would mark a significant milestone in planetary exploration. By combining mobility, advanced chemical analysis, and atmospheric studies, the mission will provide a comprehensive view of Titan's environment. If Titan's organic-rich landscape reveals complex molecules or prebiotic processes, it could reinforce the idea that life-supporting conditions may not be unique to Earth. Beyond its scientific objectives, Dragonfly also represents a technological leap. The use of a rotorcraft on another world could pave the way for future aerial missions to other planets and moons. Lessons learned from Dragonfly's autonomous flight systems, energy management, and scientific instrumentation could influence the design of future missions, potentially allowing for more dynamic exploration of places like Mars, Venus, or even the atmospheres of gas giants. Enceladus LifeFinder, a bold leap toward detecting extraterrestrial life. One of the key advantages of studying Enceladus is that it essentially delivers samples into space for free. Unlike missions that require landers or drills to reach buried environments, a spacecraft can simply pass through the plumes and collect material ejected from the ocean below. This makes the mission more efficient and allows for repeated sampling without the need for complex landing procedures. Each time the spacecraft flies through the plumes, it could gather new data, increasing the chances of detecting signs of life. A major challenge for any life detection mission is avoiding false positives. Some organic molecules can be produced by non-biological processes, such as chemical reactions that occur in the absence of life. To distinguish between biological and non-biological sources, the Enceladus LifeFinder, or ELF mission, which is still currently in the proposal stage, would use instruments designed to measure molecular structures and isotope ratios. Living organisms on Earth tend to favor certain isotopes over others, creating a distinct chemical signature. If ELF detects similar patterns in Enceladus's plumes, it would provide strong evidence for biological activity. Another important factor is the diversity of organic compounds present in the samples. Life as we know it relies on a wide range of molecules that interact in complex ways. If ELF finds not just individual organic molecules, but entire networks of interacting compounds similar to those found in living systems, it would be an even stronger indication of life. Scientists would look for molecules that exhibit chirality or handedness, a characteristic feature of biological molecules on Earth. If the organic molecules in Enceladus's plumes show a preference for one orientation over another, it could be a key biosignature. The technology required for ELF builds on the advancements made in previous missions. Instruments capable of detecting complex organic molecules have already been developed for spacecraft, like the Perseverance rover on Mars and the upcoming Europa Clipper mission. However, ELF would require even more sensitive equipment to detect faint traces of life in Enceladus's plumes. Mass spectrometers, laser-based analyzers, and high-resolution imaging systems would all play a role in identifying the chemical makeup of the samples. After collecting data, it would transmit the information back to Earth in bursts, where scientists would analyze the results over time. By analyzing the chemical makeup of Enceladus's plumes with greater precision than ever before, the mission would help refine our understanding of what conditions are necessary for life. It could also provide clues about the origins of life on Earth. There are still logistical and funding challenges that need to be addressed before ELF can become a reality. NASA and other space agencies must balance multiple priorities, and missions to the outer solar system require significant investment. However, the scientific community continues to advocate for Enceladus-focused missions, recognizing the Moon's potential as one of the best places to search for extraterrestrial life. As technology improves and interest in astrobiology grows, the possibility of launching ELF or a similar mission becomes increasingly feasible. Conceptualizing an interstellar probe, charting the unknown frontier. Designing a spacecraft capable of traveling beyond the solar system is one of the most ambitious challenges in space exploration. While the Voyager probes have already entered interstellar space, they were never specifically designed for such a journey. Their power sources are slowly depleting, and their instruments will eventually go silent. A dedicated interstellar probe, one designed to travel beyond the Sun's influence with the primary goal of studying the vast unknowns of interstellar space, has long been a dream for scientists and engineers. The question is not just whether it can be done, but how. Spacecraft today are fast by human standards, but they are still incredibly slow when measured against the vast distances between stars. The Voyager probes, despite their historic journey, are traveling at speeds that would take tens of thousands of years to reach even the nearest star system. For an interstellar probe to be truly effective, it would need to move much faster. This means finding new propulsion methods that go beyond traditional chemical rockets, which are too inefficient for long-distance space travel. One of the most promising ideas is to use a system of solar sails powered by lasers. This concept, known as laser propulsion, involves directing high-powered laser beams from Earth or from orbiting stations onto a lightweight sail attached to a probe. The photons from the laser would transfer momentum to the sail, gradually accelerating the spacecraft to speeds far beyond what current rocket technology allows. Projects like Breakthrough Starshot are already investigating this possibility, aiming to send tiny probes to the Alpha Centauri system at speeds up to 20% of the speed of light. If successful, such technology could revolutionize deep space travel and enable probes to cross interstellar distances within human lifetimes. Concepts such as nuclear thermal rockets, which use fission or fusion reactions to generate thrust, could provide sustained acceleration over long periods. A more advanced variation, known as a fusion drive, would harness the energy of controlled nuclear fusion, similar to the processes that power the Sun. If scientists can develop a practical fusion propulsion system, a probe could reach the edge of the solar system in just a few years instead of decades, making interstellar missions far more feasible. Spacecraft operating in the outer reaches of the solar system rely on radioisotope thermoelectric generators, or RTGs, which convert the heat from decaying radioactive materials into electricity. However, RTGs have a limited lifespan, and an interstellar mission lasting centuries or more would require a more sustainable power source. One possibility is miniaturized nuclear reactors that could provide continuous energy for scientific instruments, communications, and onboard systems. Once beyond the influence of the Sun, an interstellar probe would enter the interstellar medium, which remains largely unexplored. The probe's instruments would need to be designed to study this environment in unprecedented detail. Measuring cosmic rays, magnetic fields, and the composition of interstellar gas would provide insight into the nature of the space between stars, helping scientists understand the processes that shape galaxies. Communication with an interstellar probe presents another major challenge. As the spacecraft moves farther away, the delay in communication grows. A probe beyond the solar system would experience communication delays of years or even decades. This means it would need to operate with a high degree of autonomy without waiting for instructions from Earth. Advanced artificial intelligence will play a crucial role in ensuring the probe can adapt to unexpected conditions and carry out its mission effectively. In interstellar space, traditional methods of navigation using planetary landmarks would no longer be available. Instead, scientists are exploring the idea of using pulsars, rapidly rotating neutron stars that emit regular bursts of radiation, as natural cosmic beacons. By triangulating its position based on the timing of signals from multiple pulsars, an interstellar probe could determine its location with incredible precision, allowing it to stay on course even as it drifts far beyond our current range of exploration. Thousands of exoplanets have been discovered in recent years, many of them within a few dozen light-years of Earth. If a probe could be sent in the direction of a promising system, it could capture images and data that would transform our understanding of planets beyond our own. Even a distant observation of an exoplanet's atmosphere, magnetic field, or surface features could provide clues about its habitability and potential for life. To make such a mission possible, scientists must carefully choose a trajectory that maximizes efficiency. The probe would have to take advantage of gravitational assist from our biggest planets, using their gravity to gain speed and alter its course. While such maneuvers have been used before, an interstellar probe would require even more precise calculations to ensure it reaches its intended destination. There is also the question of long-term durability. A spacecraft traveling through interstellar space for centuries or even millennia must be built to withstand micrometeoroid impacts, radiation exposure, and the extreme cold of deep space. Shielding technologies, self-repairing materials, and redundant systems would all be necessary to ensure the probe remains operational long enough to complete its journey. An interstellar probe represents a fundamental step in humanity's exploration of the cosmos. The successful launch of such a mission would mark the first time that a human-made object was intentionally sent beyond the solar system with the goal of reaching the stars. While the technical challenges remain significant, the dream of sending a probe beyond the solar system continues to inspire researchers around the world. Tracing cosmic origins, proposed missions to unravel solar system formation. The story of the solar system's formation is locked in the oldest and most primitive materials still drifting through space. Asteroids, comets, and even dust grains frozen in time hold chemical signatures of the early solar nebula, the vast cloud of gas and dust that collapsed to form the Sun and its planets. To truly understand how the solar system came to be, scientists have proposed missions aimed at gathering and analyzing these ancient remnants. By studying unaltered cosmic materials, researchers hope to uncover the processes that shaped our planetary neighborhood more than 4.5 billion years ago. Several missions have already provided glimpses into the past, but future spacecraft will go further, targeting untouched reservoirs of primordial matter. Unlike planets which have undergone billions of years of geological change, certain asteroids and comets have remained largely unchanged since their formation. These objects act as time capsules, preserving the original building blocks of planets and moons. The OSIRIS-REx mission, which successfully retrieved samples from asteroid Bennu, demonstrated the value of bringing extraterrestrial material back to Earth. Bennu, a carbon-rich asteroid, is believed to contain complex organic molecules, compounds that could have played a role in the origins of life. The mission showed that asteroids can harbor ingredients necessary for life, reinforcing the idea that early Earth may have been seeded with organic material from space. Future missions aim to expand on this success by visiting different types of asteroids, especially those that formed in the outer reaches of the solar system where conditions were much colder. One proposed mission concept, the Comet Astrobiology Exploration Sample Return, or CESAR, seeks to return material from a comet's nucleus. Comets, unlike asteroids, are composed of volatile ices mixed with dust and organic compounds. They formed in the outer solar system and have remained in deep freeze for billions of years. By analyzing a sample from a comet, scientists hope to learn more about the role these icy bodies played in delivering water and organics to early Earth. Unlike past comet missions, which only performed remote observations or impactor experiments, CESAR would bring pristine material back to Earth, allowing for much more detailed analysis. Another mission concept focuses on the Trojan asteroids, ancient remnants trapped in stable orbits around Jupiter. These objects are thought to be as old as the solar system itself, and may have originated in different regions before migrating to their current positions. NASA's Lucy spacecraft is already on its way to fly past several Trojans, but a sample return mission could provide a much closer look at their composition. Scientists suspect that these asteroids hold clues about the diverse environments present in the early solar system and how planetary migration shaped the architecture of the planets. Beyond asteroids and comets, interstellar dust particles offer another window into the solar system's origins. These tiny grains, drifting through space, can be collected in Earth's upper atmosphere or captured using special aerogel collectors mounted on spacecraft. Missions like Stardust have already returned samples of cometary and interstellar dust, but new efforts aim to improve collection techniques and gather larger, less contaminated samples. By studying these microscopic fragments, researchers can trace the chemical history of the solar system's raw materials and even compare them to dust found in other star systems. Understanding the early solar system isn't just about studying individual objects. It also involves piecing together the dynamic processes that shaped planetary formation. One major question is how the Sun's protoplanetary disk evolved over time. This disk, composed of gas and dust, was the birthplace of planets, moons, and countless smaller bodies. Observations of distant young star systems suggest that such disks undergo significant changes before planets fully form, but direct evidence from our own solar system is needed to confirm these models. A proposed mission called the Interstellar Probe would help answer some of these questions by traveling far beyond the solar system's boundary. By analyzing dust particles in interstellar space, it could compare material from our solar system with that found between the stars. Such a comparison would reveal whether the building blocks of planets are common throughout the galaxy, or if our solar system formed under unique conditions. The probe would also study the remnants of the Sun's early outflows, shedding light on how stellar winds and radiation influenced the distribution of matter in the protoplanetary disk. Another critical aspect of planetary formation is the role of water in shaping emerging worlds. Scientists believe that the early Earth may have been too hot to retain large amounts of water, meaning that much of it had to be delivered later, possibly by asteroids or comets. Missions designed to analyze water-bearing minerals in ancient meteorites could help determine where Earth's water originated. If similar hydrated minerals are found on other planetary bodies, it could suggest that water-rich environments were common in the early solar system, increasing the chances that habitable worlds formed elsewhere. Looking ahead, future missions may incorporate new technologies to enhance sample collection and analysis. Advanced landers and drilling systems could allow for deeper exploration of asteroids and comets, reaching layers that have been shielded from space weathering. Spacecraft equipped with miniaturized laboratories could perform preliminary analysis of samples before returning them to Earth, ensuring that only the most valuable material is selected for study. Improved propulsion systems may also enable faster and more ambitious missions, reducing the time needed to reach distant targets. Next-generation instruments, breakthrough technologies for deep space. Space exploration has always depended on technological advancements. Every major discovery has been shaped by the tools used to make observations, measure data, and analyze distant worlds. Next-generation instruments will expand the ability to detect faint signals, map surfaces in higher resolution, and analyze the composition of planetary environments with greater precision. One area of major improvement is in spectrometry. Spectrometers are essential for determining the chemical makeup of celestial bodies by analyzing how light interacts with different materials. Traditional spectrometers have been used in space missions for decades, but the next generation will be far more sensitive. Some upcoming designs will feature miniaturized components, making them lighter and more efficient, while still providing higher accuracy. Others will incorporate new ways to scan a wider range of wavelengths, allowing for deeper insights into planetary atmospheres and surface compositions. A key advancement in spectrometry is the integration of quantum cascade lasers. These lasers can produce highly specific wavelengths of light, which can be used to probe gases with extreme precision. This technology will be especially useful for missions searching for signs of life, as it can detect trace amounts of organic molecules in the atmospheres of distant planets or in the plumes of icy moons. Unlike older spectrometers that rely on sunlight or other external sources, quantum cascade lasers actively emit light and measure how it interacts with different materials, making them more reliable in dark or shaded environments. Another breakthrough comes in the form of hyperspectral imaging. Traditional cameras capture images in visible light, and some advanced systems extend into the infrared or ultraviolet. Hyperspectral imaging, however, divides light into hundreds of bands, revealing chemical fingerprints across a much wider spectrum. This technology will allow future spacecraft to map the surface of planets, moons, and asteroids with unprecedented detail. For example, a spacecraft equipped with a hyperspectral imager could identify specific minerals on Mars or detect organic compounds on Titan, even in areas where sunlight is scarce. Spacecraft operating near the Sun, like the Parker Solar Probe, must endure intense heat, while those venturing into the outer solar system face extreme cold. Future instruments will be designed with advanced thermal regulation systems, using materials that can tolerate rapid temperature changes without losing functionality. Some new sensors will be able to adjust their sensitivity in real time, adapting to the changing conditions of space. High-resolution cameras have already provided breathtaking images of planets, moons, and asteroids, but upcoming improvements will enhance both clarity and depth. One of the most anticipated developments is the use of light-field imaging, a technique that captures not just a flat image, but also the direction of incoming light. This will allow scientists to reconstruct three-dimensional models of planetary surfaces with incredible accuracy. Another promising innovation is adaptive optics, which corrects for distortions caused by atmospheric interference or spacecraft movement. This technology, commonly used in ground-based telescopes, is being adapted for space missions. By continuously adjusting tiny mirrors in real time, adaptive optics can produce sharper images, even from fast-moving probes. Future planetary orbiters equipped with this technology will be able to capture clear images of cloud layers, surface features, and even geological activity. Some of the most exciting instrument designs focus on direct life detection. Unlike past missions that have mainly searched for habitable conditions, future spacecraft will carry tools specifically designed to find biological signatures. One such tool is the Life Detection Microscope, which will use advanced fluorescent dyes to highlight organic compounds in collected samples. This instrument will be crucial for missions to Europa and Enceladus. By examining these samples under high magnification, scientists may be able to identify complex molecules that indicate the presence of living organisms. Another revolutionary concept is the use of nanotechnology-based sensors. These tiny devices, often no larger than a grain of sand, can detect individual molecules with extreme sensitivity. They can be placed on robotic landers or aerial drones, scanning the environment for signs of biological activity. Because they require very little power, nanotech sensors could operate for extended periods, continuously collecting data without the need for frequent maintenance. AI-powered systems will help future missions process vast amounts of data more efficiently. Instead of waiting for instructions from Earth, spacecraft equipped with AI can analyze data in real time and make decisions on which samples to prioritize. For example, a rover on Mars could use AI to identify promising rock formations, adjusting its exploration path based on previous findings, maximizing the chances of discovering something truly groundbreaking. The ability to explore deep space is also being enhanced by improvements in communication systems. Future missions will use laser-based communication, which allows for much faster data transfer than traditional radio waves. By sending information in tightly focused beams of light, laser communications will enable spacecraft to transmit high-resolution images and complex data sets back to Earth more efficiently. This will be especially important for missions beyond the solar system, where signal delay and bandwidth limitations pose significant challenges. Another key area of development is in drill and sampling technologies. While past missions have used relatively simple drills and scoops to collect material, new designs will allow for deeper penetration into planetary surfaces. One promising approach is ultrasonic drilling, which uses high-frequency vibrations to cut through rock without requiring excessive force. This technique will be valuable for missions aiming to access subsurface ice on Mars or Europa, where buried layers may contain preserved organic compounds. Some proposed missions will also include molecular analyzers that can process samples on site. These compact laboratories will use a combination of chemical tests, spectroscopy, and chromatography to determine the composition of collected materials without needing to return them to Earth. This will greatly expand the range of what can be studied during a single mission, reducing reliance on sample return programs. The search for extraterrestrial life is driving the need for even more sensitive instruments. One promising technology is the lab-on-a-chip system, which miniaturizes complex chemical analysis tools onto a tiny silicon chip. These devices can process liquid samples in real time, detecting amino acids, lipids, and other biological markers. Because they are small and require little energy, they can be integrated into landers, rovers, and even autonomous underwater drones designed to explore the oceans of icy moons. Even instruments designed for space telescopes are undergoing major improvements. The next generation of space observatories will use ultra-thin, lightweight mirrors that can be precisely adjusted to improve image quality. Some proposed designs involve segmented mirrors that can fold and unfold in space, allowing for much larger telescopes than what is currently possible. These advanced optics will allow astronomers to directly image exoplanets and analyze their atmospheres for potential signs of life. Future deep space missions will rely on a combination of these cutting-edge technologies. With each innovation, space probes will be able to travel farther, see clearer, and detect more than ever before. CubeSats in deep space: how miniaturization is expanding our reach. CubeSats are changing the way space exploration is conducted. These small, box-shaped satellites, often no larger than a shoebox, are proving that advanced technology does not always have to come in massive, complex spacecraft. Once confined to low Earth orbit for educational and technology demonstration purposes, CubeSats are now making their way into deep space, complementing larger missions while exploring new frontiers on their own. Their ability to perform meaningful science at a fraction of the cost and size of traditional spacecraft is reshaping how scientists approach space exploration. The shift toward miniaturized space technology has been driven by advances in materials, electronics, and software. Unlike traditional satellites, which can take years or even decades to develop and launch, CubeSats can be designed, built, and deployed in a much shorter time frame. This has made them appealing not only for universities and private companies, but also for major space agencies. NASA, the European Space Agency, and other organizations are increasingly integrating CubeSats into larger missions, using them as secondary payloads that can piggyback on rockets carrying larger spacecraft. While traditional deep space probes can cost billions of dollars, CubeSats can be built and launched for a fraction of that price. This cost-effectiveness allows for more frequent experiments and a higher tolerance for risk. If a CubeSat fails, it is far less devastating than the failure of a full-scale mission. This encourages innovation, enabling researchers to test new concepts that might be too risky or expensive to attempt on a conventional spacecraft. The Marco mission was a landmark moment for CubeSats in deep space. These two small satellites, known as Marco A and Marco B, were launched alongside NASA's InSight lander in 2018. As InSight made its journey to Mars, the Marco CubeSats traveled independently, relaying crucial data back to Earth during the lander's entry, descent, and landing. This marked the first time CubeSats had ventured beyond Earth orbit and played a direct role in a planetary mission. Their success demonstrated that even small satellites could provide valuable support to major missions. Following the success of Marco, CubeSats are being considered for an increasing number of deep space applications. One promising area is their use in lunar exploration. NASA's Artemis program, which aims to return humans to the Moon, is planning to deploy multiple CubeSats to gather information on lunar conditions. Some of these small satellites will measure space weather, while others will scout for water ice in shadowed craters near the lunar poles. Their findings could inform future human and robotic missions by identifying key resources and potential hazards. Beyond the Moon, CubeSats are being developed for missions to asteroids, planets, and even interstellar space. One such project is the Near-Earth Asteroid Scout, a CubeSat designed to study small asteroids close to Earth. This spacecraft will use a solar sail. Its lightweight design allows it to reach its target with minimal fuel, demonstrating how CubeSats can be used for long-duration missions far from Earth. The CubeSat for Solar Particles is designed to monitor solar radiation and charged particles in deep space. By collecting data on space weather, it can help scientists understand how solar activity affects both spacecraft and human explorers. These observations are critical for planning future crewed missions beyond Earth orbit, as exposure to high-energy radiation is one of the biggest challenges facing astronauts traveling to Mars and beyond. One of the key factors driving the success of CubeSats is the development of highly efficient miniaturized instruments. In the past, scientific instruments required large, bulky components to operate effectively. Today, advancements in sensor technology, computing power, and communication systems allow small satellites to carry sophisticated equipment capable of performing tasks once reserved for full-size spacecraft. High-resolution cameras, compact spectrometers, and even miniature propulsion systems are now standard features on CubeSats, enabling them to conduct detailed scientific observations. The use of CubeSats in deep space is not without its challenges. Their small size means that they have limited power and fuel, restricting their ability to adjust their trajectories or operate for long periods. Communication can also be a hurdle, as their antennas and transmitters are much weaker than those on larger spacecraft. To overcome these limitations, engineers are exploring ways to make CubeSats more self-sufficient. One approach is to develop autonomous navigation systems that allow these satellites to make real-time decisions without relying on commands from Earth. Another strategy is to deploy CubeSats in swarms, where multiple small satellites work together as a coordinated network, sharing data and distributing tasks among themselves. Despite these obstacles, the future of CubeSats in deep space looks promising. Missions that were once too costly or complex may become feasible with fleets of CubeSats, working alongside larger spacecraft to provide a more comprehensive picture of the solar system and beyond. Proposals targeting the mysteries of the Oort cloud. Unlike the Kuiper Belt, which contains well-known objects such as Pluto, Haumea, and Makemake, the Oort cloud is so distant that no spacecraft has come close to reaching it. Even the two Voyager probes are still only a fraction of the way to its outer edge. However, interest in exploring this region is growing, and several mission concepts have been proposed to help unlock its secrets. One of the biggest challenges in sending a spacecraft to the Oort cloud is the sheer distance involved. The closest estimates place its inner edge at around 2,000 astronomical units from the Sun, more than 50 times farther than Pluto. Reaching such a destination with current propulsion technology would take centuries. To make an Oort cloud mission feasible, scientists are exploring alternative propulsion methods. One proposal that has gained attention is the interstellar probe concept. Designed to travel beyond the solar system more efficiently than previous missions, this spacecraft would aim to study the transition from the Sun's influence to interstellar space. Although its primary goal would be to observe the heliosphere and the interstellar medium, it could also provide valuable insights into the objects that populate the Oort cloud. If it were to pass through this distant region, it could potentially capture data on unseen icy bodies and help confirm the cloud's structure. Another idea involves sending a dedicated probe specifically to an Oort cloud object. This mission would require identifying a suitable target in advance, possibly by using next-generation telescopes to detect an object on a path that allows for intercept. Such a mission would need to be carefully planned, as an Oort cloud object would likely be moving at high speed and at an extreme distance. Even with a successful interception, sending back data from such a remote location would present communication challenges. Scientists would need to design highly efficient transmitters and rely on powerful ground-based antennas to receive even weak signals. Recent discoveries of interstellar objects passing through the solar system have further fueled interest in Oort cloud exploration. When Oumuamua and Comet 2Y/Borisov entered the solar system from interstellar space, they provided a glimpse into the kinds of objects that might exist beyond the Sun's gravitational reach. Some scientists theorize that the Oort cloud may contain not only ancient solar system relics, but also interstellar visitors that were captured by the Sun's gravity over millions or billions of years. A dedicated mission to the Oort cloud could help test this theory by analyzing the composition of its objects and comparing them with known solar system bodies. Since Oort cloud largely unchanged since the solar system's formation, they may hold clues about the materials that were present when the planets formed. A mission that could sample the surface of an Oort cloud object, a unique look at some of the most pristine material in the solar system. Another exciting possibility involves using an Oort cloud mission to study the boundary between the Sun's influence and interstellar space. Understanding this transition zone is important for astrophysics, as it helps scientists learn how stars interact with their environments. A probe sent to the Oort cloud could serve as a valuable platform for studying how the solar wind behaves at extreme distances, shedding light on how similar processes occur around other stars. If a spacecraft could be designed to last for many decades, or even centuries, it might eventually reach and study this distant region. Some researchers have even proposed multi-generational space missions, where a probe is launched with modular upgrades in mind, allowing future spacecraft to dock with and enhance the original mission as technology advances. Private sector ventures, commercial innovations in the final frontier. For decades, space exploration was almost exclusively the domain of national governments. Agencies like NASA, Roscosmos, ESA, and CNSA shaped the progress of spaceflight, overseeing every aspect of mission design, funding, and execution. However, the landscape has begun to change dramatically. Private companies are no longer just contractors supplying parts or services to government agencies. They are becoming full-fledged players in deep space exploration. From advanced propulsion systems to commercial lunar landers, these companies are accelerating innovation in ways that would have been unthinkable just a few decades ago. One of the most well-known pioneers of commercial spaceflight is Elon Musk's SpaceX. While much of its success has come from launching satellites, cargo, and astronauts into low Earth orbit, the company has set its sights on destinations far beyond. The Starship vehicle, currently under development, is designed for deep space missions, with the long-term goal of sending humans to Mars. Unlike traditional government programs that rely on complex, multi-phase development cycles, SpaceX has adopted an approach of rapid iteration. By building, testing, and improving designs in short timeframes, the company has managed to develop fully reusable rockets and push the boundaries of what private spaceflight can achieve. Blue Origin, founded by Jeff Bezos, has also turned its attention toward deep space. The company is working on its own heavy-lift rocket, New Glenn, which could support interplanetary missions. Additionally, its Blue Moon lander concept is being developed with an eye toward commercial lunar operations including resource extraction. Blue Origin envisions a future where private industry plays a key role in establishing a permanent human presence beyond Earth. Unlike SpaceX's rapid development style, Blue Origin has taken a more methodical approach, focusing on long-term sustainability. Beyond the well-known names, many other companies are pushing deep space exploration in new directions. One key area of focus is small-scale interplanetary probes. Companies like Rocket Lab have introduced low-cost, high-efficiency spacecraft that can be deployed quickly and affordably. The Photon spacecraft, for example, is a small satellite platform capable of supporting science missions in deep space. By making interplanetary exploration more accessible, companies like Rocket Lab are enabling universities, research institutions, and even smaller nations to conduct their own deep space missions. Commercial landers and robotic explorers are another major frontier. NASA has partnered with several private companies through its Commercial Lunar Payload Services, or CLPS program, an initiative designed to support lunar exploration through commercial means. Companies like Astrobotic and Intuitive Machines have developed lunar landers, offering a model for how private industry can work alongside government agencies. Some companies are even exploring ways to use similar landers for Mars and asteroid missions, potentially creating a new market for interplanetary cargo delivery. The private sector is also driving innovation in space resource utilization. Companies like Transastra and iSpace are investigating ways to mine water ice and other valuable materials from asteroids and the Moon. The concept of in-situ resource utilization has long been studied by government agencies, but commercial ventures are now looking to make it a reality. If successful, these efforts could dramatically reduce the cost of space travel by providing fuel, water, and building materials directly from space, rather than launching everything from Earth. Another key area of private sector involvement is advanced propulsion. Traditional chemical rockets remain the backbone of space exploration, but they have significant limitations when it comes to deep space travel. Private companies are exploring alternatives, including nuclear propulsion, solar sails, and ion drives. Companies like Ad Astra are working on plasma-based propulsion systems that could make long-duration missions faster and more efficient. Breakthrough Starshot, a private initiative backed by venture capital, is developing a concept for laser-driven light sails that could one day propel tiny probes to interstellar destinations at a fraction of the speed of light. Commercial ventures are also reshaping space communication infrastructure. Traditional deep space missions rely on large ground-based antennas, but private companies are looking at new ways to establish high-speed data networks beyond Earth. Companies like SES and Telesat are developing satellite constellations that could one day extend deep space communication capabilities. Meanwhile, SpaceX's Starlink project, while focused on Earth-based internet coverage, has the potential to evolve into a network that supports missions throughout the solar system. Historically, deep space missions have relied entirely on government budgets, which can be unpredictable and subject to shifting political priorities. Private companies, on the other hand, have the flexibility to seek independent investment. Some firms are exploring commercial sponsorship models, where deep space missions could be partially funded by corporate partnerships. Others are looking at potential revenue streams such as space tourism, media rights, or resource extraction. Deep space missions require high levels of reliability, and unlike government programs, private companies must balance profitability with scientific goals. Additionally, there are ongoing debates about how commercial activities should be regulated in deep space. While the Outer Space Treaty establishes certain international guidelines, it was written in an era when space exploration was strictly government-led. As private companies begin operating on the Moon, Mars, and beyond, legal frameworks may need to evolve to address issues such as resource ownership, liability, and the environmental impact of commercial activities in space. The collaboration between private industry and government space agencies has led to a hybrid model of exploration. NASA, ESA, and other agencies continue to lead ambitious deep space projects, but they are increasingly relying on commercial partners to supply key technologies, launch vehicles, and even entire mission components. This approach allows for greater flexibility and cost efficiency, as private companies can often develop solutions faster and at a lower cost than traditional government programs. As private space ventures continue to grow, they are opening up new possibilities for exploration. Missions that were once thought to be too expensive or technologically complex may now become viable. Commercially operated space telescopes could survey distant exoplanets. Privately funded rovers could explore the icy moons of the outer solar system, and asteroid mining operations could provide resources for deep space habitats. By bringing in new ideas, capital and competition, private companies are playing an increasingly important role in shaping the future of space exploration. Has this deep dive into the remarkable milestones humanity has achieved so far inspired you as much as it has inspired us? What topic would you like for us to cover next? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.